这边要不然上下翻一下你的 screen 看看。我这边 OK 可以。Okay, so welcome everyone again for the afternoon section. So in the afternoon, we'll mainly have speakers from industry and also startups to discuss more from the industrial perspective about what's next in visual generative modeling after diffusion, for example. And the first speaker will be Jiaming Song. So Jiaming is the CTO, I guess, or the chief scientist in Luma AI. And he also previously was the first author of DDIM. So he is definitely the representative from diffusion models. So we'll hear about what he's thinking about what's after diffusion models from the talk. So, Jiaming.
Okay, yeah, thanks for the invite. And yeah, I'm going to talk about a bit more on the technical side on like how do we think about what's beyond diffusion model from a inference perspective. To set some things up, diffusion models has definitely been very, like influential, and like actually exactly 1 year ago today, like at Luma we released Dream Machine. You can see the date on like June 12th. So that's actually like just 1 year ago. So if you think about it, like being commercially viable or like general accessibility, high quality video models is only a year, and across the year we have seen a lot of interesting developments throughout this this space. And the after this year, of course, the quality of the video models has increased by a lot. But during this time, like people are not just interested in only text to image or text to video. People are interested in more of this like native multimodal generation. I call it the current hype, but I think it's a real thing that people are very interested in. So on the left side is a figure from the Chameleon paper from Meta. So it shows you this, prompt response structure where the response and prompt can contain like arbitrary like interleave sequences. So interleave image with text in this case. And it signals a very different approach from what has been pretty mature in the sense of visual language models and diffusion models to these like interleave models. Of course, what is very different is not the input, because both type of models can take inputs that are interleave sequences. So with the vision language models, obviously, and with diffusion models, you can also take in like interleave sequences of images and text, but the output is the image. Of course, with interleave models, the most difference is that you have to handle like interleave sequence in and interleave sequence out. So there has been already a lot of papers like since last year, like Chameleon was the one of the early ones. But most of these like papers are based on different loss functions that are combinations of discrete autoregressive models or next token prediction, or discrete diffusion or continuous discrete diffusion. So for example, Chameleon takes this discrete autoregressive, and image space is also discrete autoregressive. There's also the case where images uses discrete diffusion, image uses continuous diffusion, or like everything uses discrete diffusion. So basically it's like, well, you can easily crunch out different papers by combining these like elements, and of course based on the algorithms that like work quite well. Of course, I have more time to talk about. I don't have more time to talk about the discrete case, although I also have some ideas on it. So today we're talking more about like what's next after diffusion. So let's talk about the problem of diffusion a bit more. So of course in this setup, the continuous tokens in the diffusion model, I hope I don't need too many introduction. That diffusion model tries to denoise a noisy sequence from the top image on the right towards the data, and or generates like realistic samples. And you can combine this with a like autoregressive model in the text space and like do the prediction part. So for example, this is the architecture diagram of this like recent paper from ByteDance called Bingo, where you have this like mixture of transformers with discrete tokens acting on the text part and continuous tokens acting on the image part. So it actually has a, it's not actually just that. So while the sequence looks like this, where you can interleave a discrete tokens with a continuous token, discrete tokens with continuous tokens, The compute on the hardware is actually more like you compute the discrete tokens. That's pretty straightforward. It only requires like one pass of the transformer. However, with the continuous tokens, it may take like many passes of the transformer. So because of the nature of like diffusion models. So in this case, it's a bit of a problem because as everyone wants to not spend too much compute on these options. Of course, there also has been like distillation methods being developed for this purpose precisely, but a lot of these methods are not necessarily like very stable, or they're not the type where you can just like write the loss function, like run it overnight, like go to bed, forget about it. So only discrete autoregressive model and continuous diffusion model are kind of these like category, and that's why the current field has been dominated by the two algorithms. But if you think about it, like none of these are super perfect if you are trying to adapt this to a multimodal interleaved generation case, and also these algorithms are kind of like 5 years old in popularity like standpoint. So GPT-3 was published 2020 of May of 2020, and then the first paper that popularizes diffusion models called DDPM, which was also published around June of 2020. So these algorithms has been around for 5 years, and since then, of course, there has been a lot of like incremental improvements on these, like for example, like flow matching, but none of them are like kind of like fundamentally changing the paradigm. So again, back to continuous generative models, like if we like view the history of the continuous generative models in general, there has been this kind of like a trilemma. So ideally we want the generative models to be stable to train. They generate a very high quality samples, and they also have like very efficient inference. And as the we haven't characterized all the algorithms in this domain, but here's like a very popular like a round of algorithms. So for example, for like variational autoencoders and normalizing flows, they were like pretty early around like 2015 and 2013, and they train pretty reasonably stable because it is just maximum likelihood, and their inference is just like 1/4 pass of the network. So they enjoy these, but their sample quality is kind of bad. For GAN and some type of like distillation methods with scans, you have like high quality samples and efficient inference, but some of the cases it doesn't train like in a very stable fashion. In diffusion models, it's the other axis. So it has high quality sample, training is very stable, but the inference is not necessarily so very efficient. So essentially we need something there, and basically something around like training stability, like high quality sample, efficient inference, and of course this is something that a lot of people want. And like actually like Arash, who's like just come in there, he had some like paper was on the like diffusion GANs, which is actually also a very like great inspiration of like my work on this case. But in any case, like people want to solve these issues. And I guess the question is like, if we can manage to achieve the algorithm that, addresses these issues, maybe we can break the algorithm ceiling of, autoregressive models and diffusion models. And in turn, maybe this algorithm can be used to train on like more data and perhaps break the, pre-training like wall as we currently like see it. So yeah, like I hope to kind of have more like better algorithms that, break the ceiling of like pre-training. So I guess this now comes to the real part of the actual talk, which this will be like organizing these points. So first I will talk about two things that might seem to be quite trivial, which are the two axes of like inference scaling. And the second point is like maybe more of my personal opinion is to like think about these like algorithms from an inference perspective. So think about how they would work in inference and whether they make sense at inference time before working on the training algorithm. And three is the third point is like starting from this perspective, like analyzing like why DDIM, which is the thing I worked on 5 years ago, and also by like extension, diffusion is like naturally suboptimal, like regardless how we train it. And I guess the final point is to kind of like inspire how we might be able to kind of like do something that is like newer than diffusion and break the current like ceiling. So how do we scale at inference time? Inference time, like test time scaling or inference time scaling has been very popular in the language like model domain. So here I'm just going to list two of like maybe trivial statements here, which is, well, either we increase the number of tokens or we don't increase the number of tokens. Like this covers like literally every algorithm. Of course, this kind of categorization has its like actual like dependencies. So in the case of like increasing the number of tokens, this is very natural. So you have the like language model Liang, where you try to like have chain of thought, which is one way of like increasing the number of tokens being used. You can also do like chain of thought with like reasoning data, and you can also do like reinforcement learning on top of these cases. And as you can see, oftentimes increasing the sequence length at infinite time will make the models better at like many tasks, including ones that are like, for example, math and programming. So scaling the sequence length definitely helps. If you don't scale the sequence length, yeah.
So can you make sure you're sharing your screen? Just do it again, because they weren't getting it. And then mute and unmute your microphone. Okay. All right, thank you.
Okay, all right. Yeah, so basically, you know, in the case of not increasing the token number, but also like doing inference type scaling, like diffusion and flow matching is a very natural way of doing this. So basically, the way you do this is that by denoising on the same set of like tokens, you are refining the result and generating something from like, you know, not a very good looking image to something that looks good. So this doesn't like each iteration doesn't like increase in terms of computational complexity, like language models. So this is kind of like not increasing the number of tokens. Of course, there's like algorithms that stand in between. You know, in this case, for example, you have a autoregressive like diffusion model where autoregressive is the outer loop, but diffusion model is the inner loop, or you have a like a multi-resolution like diffusion model where you can think of the resolution itself as kind of like a token space or sequence space. But there are methods that kind of lie on both axes, is what I'm saying. Of course, you know, in the case of like diffusion models, you know, there also has been work showing that you can increase the number of like function evaluations to get like better properties by scaling this. However, I think, you know, of course, you know, you can also write papers just by like scaling up like test time compute, and that's also a very easy way to write the papers. You know, but of course, you know, like for practical reasons, you don't actually just want to be able to scale compute, because that depends on your like computational like capacity. If you don't have a lot of like compute, you won't be able to do this. So you actually have to like kind of scale like efficiently while using the more compute. If you don't do that, then, you know, in theory, people can make this like infinite monkey arguments that you can just get infinite number of monkeys, get them to like type random things like at space in like infinite amount of time, and eventually they will generate a sequence that is comes from Shakespeare. So of course that is like a way of scaling, but it's a very inefficient way of scaling. And I think like from time to time we have seen how like we have made advances in algorithms by scaling more efficiently. So one example that's very you know, like famous is like AlphaGo. So basically, you know, instead of just doing search, which kind of solved chess, they need to have like, you know, reinforcement learning plus like using like CNNs or deep neural networks to model the policy and value functions, so that you know, the search process gets more efficient. So it's not just if we only use brute force search, then even with the current amount of compute, it will be quite difficult to like solve like Go. So scaling efficiency is definitely very important. So here I list like two positions of the talk. So first is that, well, eventually if we want to develop the, you know, like pre-training algorithms, the inference algorithms of that will need to be able to scale in both axes, whether, you know, both in terms of like extending the sequence length by running with more tokens and refining existing tokens. The second point I also just made just now, which is that it should be efficient. And by efficient, I define as such. So assume that your model has enough capacity, and this is only under universal approximation theorem. So basically, your transformer is a model that is in theory able to fit any function, not distribution. It should use like as few kind of steps to like get to the solution. This is the efficiency part. The third part is actually to analyze the inference algorithm before analyzing the training algorithm. And you know, my argument is that like, you know, despite there has been a lot of different ways to train the model, there is not that many ways to kind of do inference on the model. And like being able to analyze this, whether it makes sense on like points 1 and 2, is going to be helpful to see like the limitations of diffusion models. Again, this argument applies to both the continuous and discrete cases, but I will focus on continuous today. So if you look at like continuous diffusion, this, you know, the first checkpoint that definitely works. So for example, the diffusion does scale in the refinement axis. And this is very different from, like methods such as like GAN and like normalizing flows, in the sense that, it wasn't designed to scale in the inference time. This also benefits in the sense like, well, if you can just choose to train maybe a small model and kind of like compensate that at inference time to get to like reasonable quality. The second point is not the case, because in diffusion models, even if you train your model with the infinite capacity, the training objective itself is trying to match the like mean, like some kind of like a mean expectation of the data distribution. So in this case, it doesn't matter whether how big your model is not going to like give you the right results in one step. On the other hand, like people might ask, okay, maybe I can train a one-step like generator model, and like still this should give me results in one step. But then the problem will be that if you have such a model, then it won't be able to like generate the right distribution in like infinite number of steps. But I'm arguing that the right algorithm should be able to do both. So you should be able to kind of generate in one step, and you also should be able to generate in like multiple steps. From now, I'm going to show like how DDIM is actually kind of not the right inference algorithm in this sense, regardless of how it's trained. You can train it with diffusion model, you can train it with like a GAN objective, you can train it with something else. It doesn't matter. So why is this the case? So if we look at this, consider this like figure where the left side is the data and the right side is the prior distribution. So and from the x-axis is basically the time axis in diffusion models, and the y-axis is the samples at the diffusion models. So basically, you are trying to kind of flow from the prior distribution into the data distribution via like iterative like solving this case. So at each point in time where and the location, I'm going to use the diffusion models to make a prediction. And people can argue whether this is like a mean prediction, like epsilon prediction, or like velocity prediction. It doesn't matter. It's just different parameterizations. But you are trying to make a prediction, let's say just an x0 like prediction, the noise prediction. And in DDIM, what you're actually doing is that from your starting point, you make a prediction, and you're trying to get to the next step by interpolating between these two. So basically, the model chooses, the model doesn't know which is the next step is going to be yet. And we only choose that in a like post hoc fashion. So while your model has infinite capacity, potentially with regard to the starting location, it doesn't actually have the information regarding the end location. And if you take the DDIM like update equation and take the partial derivative over S, which is the endpoint, it's actually just a linear function, which means that you're just only able to represent a linear interpolation between these two. And if you're able to train a model such that it generates the right distribution in one step, so it maps from the prior distribution to right samples in one step, then this interpolation will surely get wrong somewhere when you're trying to like do this like n step sampling. So this is a bit of an issue. A fix is actually quite easy. So because our model doesn't really know what is the endpoint, and that limits the capacity of the model, you could just add another like time step into the model. So basically now, instead of just knowing about where you're starting at, you also know where you are where you end at. So basically, this allows you to have the model cover like more complex solutions, such as like integration with like the probability flow OD. And in fact, you can do this by the regular diffusion model is just a special case where your start point is equal to the endpoint. Again, this is a very simple fix, and it actually is, has been in the literature, being proposed for different training approaches differently. So I'm trying to argue is that well, once the inference algorithm is decided, you can actually have very different approaches to train with very good efficiency. So for example, one of the earlier works is called the consistency trajectory models, which introduces this idea. And shortcut models also is one of such methods. And there's also this term called flow map matching. And very recently, I think it's either this month or earlier, late last month, it's the mean flows for one-step generative modeling. They are all based on similar ideas. Of course, with the time we have, I'm going to go more into our own paper called the inductive moment matching, which is works done by Lin Qizhou, who's also here in the room, and with me and with Stefano, and we did this at Lumina. So this also recently got into like oral in ICMO, and because of the, I guess, the results. So what's quite interesting in like inductive mode matching against other methods that we listed earlier is that it actually has not much of a connection with diffusion models if you think about it, except for how it is like sampled. So it's not actually dependent on the denoising score matching or flow matching. It doesn't depend on the score-based stochastic differential equations. And even the solution that we get does not have to be connected at all to the probabilistic ODE. And we can actually find proofs for that. But the method itself is actually quite simple. So instead of trying to, if you know about consistency models, you're trying to kind of like have two like ways of approaching the two different approaches of like achieving, like getting to the same point. So instead of like doing consistency in points, we are trying to get consistency in distributions. So for example, here I have like 3 time steps where T is the more noisy one, and R is the medium one, and X is the like final one. So I have 2 ways of getting to S. So I can go from like T to S, or I can go from T to R and then the R to S. So I basically have 2 ways of like generating like points of excess. Of course, these 2 ways of generating distribution should be close. So basically, all we are doing is trying to use distribution like matching loss to minimize this loss function. And instead of using like GAN, which is commonly the thing that people do, we can actually use moment matching, or more specifically, something called the maximum mean discrepancy, or MMD. This is also something that's like proposed more than 15 years ago, and like people have been using it in like deep learning for like at least 10 years in the case of generative moment matching networks. So if to people who haven't heard about this, so it's very similar to GAN in the sense that it has a discriminator. But unlike GAN, it uses a special family of discriminator called reproducible kernel Hilbert space. So basically, it's a special class of discriminators. And the benefit of this is that you don't actually have to optimize the discriminator or like optimize in the inner loop via gradient descent. The optimal solution has like already been given in like kernel form. So basically, you can just like list out, like write the optimal solution in the mathematical form. So there's actually no optimization of the discriminator. So like you can only just train the generator. So training is like somewhat stable with like more samples. And therefore we have reached this algorithm, which has like multiple like advantages. So first of all, it has a single stage training and a single objective function. I would say this is not my point is not to show that only a single objective function like is the thing to do, but it is possible to train like models with like simple things like this. Also, it actually generalizes consistency models in the sense that like where consistency model is a special case where you're comparing distributions with only like one sample. Of course, comparing distribution with one sample is kind of suboptimal. So this also kind of explains why sometimes like training with consistency models is not necessarily as stable as it seems to be. And of course, we instead achieve pretty like good stability when training the models. And like last but not least, we also reaches like state-of-the-art like few step generation. But not only that, one thing that's also kind of interesting is that like, as we increase the number of steps, we still get like state-of-the-art results or even improve upon the few step results. So a mental model that we can think about like for diffusion models versus like inductive moment matching is that as you increase the number of steps, the diffusion models and the inductive moment matching reach roughly the same optimal like location in terms of sample quality. But the few step results in inductive moment matching is better. So basically, this method allows you to get better quality if you throw more compute at it, or if you don't want to throw more compute, it has like better sample quality results. So here's a graph showing that the training is kind of like relatively stable across like different iterations, like consistency models. And we also show like results, good FID results in these cases. If you're interested, you can look at the details. We did experiments on CVPR10 as well as like ImageNet. These are all pre-trained, so there's only a single objective, and it's not like multi-stage like distillation and such. And obviously, it also like scales. So if you have like train it on bigger models or train it for longer or like use more sampling compute, you get better results. And you can actually chart this in this like Pareto optimal frontier where you ideally want to use less sample compute and you want to get lower like a facial inception distance. So basically on the lower left axis is what you are trying to get at. So I think IMM is actually on pretty much on this like efficiency quality frontier, based on when we published the paper. So yeah, that's all in all. And like again, back to where we are trying to solve with the continuous generative model, diffusion models being one of them. We want to solve the issue of training stability because that's the algorithms that eventually will be popular. We want to get high quality samples, and we want to get efficient inference. And so IMM and also possibly other flow map methods could actually be a very promising direction to this approach. And again, I'm mostly arguing the point of like adding another time step in the inference time algorithm. But again, like I said, there can be like many more different algorithms to train it, and I'm okay with like different methods to train it. And if you're interested in the like method or the positions on like inference time training, here are some of the links. We have released the inference code, but we will also release the training code soon around like ICML time. And here's also the position paper. But the code base also has a link to the paper as well as like some blog posts that explains the idea. So I won't list it here. So yeah, I think that's it for my talk. And yeah, if you're interested in working on some of these like frontier research and also developing models for this scaling these up, please join us. And we also have a happy hour today at like Bar Stew. I think it's around like 6 p.m. on this link. So yeah, if you're interested, you're welcome to join. Yeah, thanks.
Okay, so since we have maybe an additional 5 minutes, like we're welcoming like questions or any sort of like want to communicate with Jiaming.
Hey, thanks for this amazing talk. Really cool insights into the moment matching paper. You mentioned before that this moment matching loss is only really stable if you have like lots of samples in the training batch. This is like a problem in practice. How many GPUs do you minimally need to train this?
So I think the number of samples we did ablations on this. So 4 is enough. So basically, your batch size is going to be like, well, like, but I guess you can also choose to not do that. So for example, suppose you have a regular batch size of 16 in, let's say, training a diffusion model. You can then instead choose a batch size of 4 in our case, and each batch size of 4 have like 4 samples. So computationally wise, it's like roughly, it's on the, it's not that much worse. Yeah, you can certainly train this with existing amount of hardware. And I think most of our experiments are also just done with like in these cases like 1 or 2 nodes. So it's not like okay, we need like hundreds of nodes to run this. There's still like ImageNet scale experiments they can run.
Thank you.
Yeah.
Yeah, do you have any other questions? Okay, if not, let's welcome the next speaker. Should be Jiatao. Yes, he's here. Yeah.
I can turn off the screen structuring. Right?
Yeah, and again, like thanks, Jiaming, again for.
I'm locked out from my room. What's the number? 9:15. Japan, yes. So you need new keys. Sure. Hello. What is your ID? Check it. Last name. I have a photo of it. Yes, whatever that you have. The photo. One is enough.
And also share your screen.
Okay. This can be extended, right?
No, so you cannot, like, you have to also like plug in to this one. So this one is the Zoom. So you may need to also put your screen there. So
Sorry, I wasted all the time.
no,
Jiaming
it's
said.
totally fine. Yeah, so okay, so now we're ready for Jiatao. So Jiatao is now a researcher at Apple and also an incoming assistant professor in UPenn. So he will be talking about how do we revive normalizing flows in 2025. Please.
Okay, thanks Tim for the very nice introduction. I'm Jiatao. I also gave the similar talk yesterday. I would like to just advocate one idea is to train, in 2025, we can also still train scalable normalizing flows. So, but in the beginning, I was just starting with this. And right now we have the two worlds of generative AI. So we have autoregressive model, which basically working in the discrete space, like a language model, predict token from left to right, one to another. But on the other hand, as this workshop's title, we have the diffusion of metric-based models where you're starting from random noise iteratively refined images. So it's basically also aligned what Jiaming's talk about the two lines of scaling models. So for diffusion of metric-based models, you simply can be trained by you first have an image, you add noise on that, and you learn a denoiser to denoise the noisy images. And in inference time, you start from left to and the iteratively refined images. It's getting incredibly successful and becoming the state of the art for all kinds of visual generation, like image and videos. But on the other hand, language models is very successful. Everyone was using these kind of things. It's also being a hot topic right now. People using autoregressive model to generate images as well. For example, you can first train encode decoder mapping image into discrete tokens and just run everything like a language model. And this may be also the techniques behind the very successful ChatGPT image generation models, where in their reports, they explicitly mentioned this model is an autoregressive instead of a pure diffusion models. And that maybe the past is doing that thing in the interlinked models.
Can I please get the
But all these
small,
methods, if you require on this
latte,
presentation, is
I
inevitably
like it
you
in that
have
8 ounce
performance
cup.
loss when the edits.
Yeah.
It'll be
So
to
one
go.
potential way is
Yes,
maybe
of
you
course.
can add the
Do
same
you have a milk
together,
preference?
like a combining
No,
autoregressive
Just
model
regular.
with
regular.
diffusion.
Is
For
that all right?
example, in
Yeah,
our last year's
and I'm thinking,
neuroscience paper, we showing that we can actually
that's
connecting two models where you first give a prompt to let the language model to generate associated tokens, like a latent planning, and based on the planning, you have a diffusion to generate the images and like connecting them.
Yeah.
But to me, I mean, this kind of method is not satisfactory because it just simply have two methods and combine them together. It's not like a real unified models. So what might be the better unified models? Another approach I think now the people have thinking about is, can we also using autoregressive model to model in the continuous space? For example, what Tian Hong's very famous paper, the MAR, and also there's some other paper doing diffusion forcing XAR, where basically you can think about it's like you have a two loop. In the outer loop, you have an autoregressive model running patch by patch or frame by frame, and each patch you have additional diffusion iterative refinement and based on different conditioning. We also have a similar paper as well at iClear we presented. It's called DART. You can think about it's just simply reverse this order where you have an outer loop is a diffusion-like models, where in the inner loop you have autoregressive model. So you can basically doing similar things and kind of achieving the both like generation in different axes. But the core problem to me is like if you want to using autoregressive model continuous space, there's two core problems. One first is you want to find a very powerful function to capture the complexity of the distribution, like a multimodal distribution where people using diffusion model. And second is we need to better minimize the test test mismatch. So yeah, I'm basically discussing about the background where these kind of two words, and there's also a lot of research trying to unify these two words to have a uniform combining these two things. In 2022, there's a very famous workshop was led by Arash at the time, is talking about but it's a lot of noise.
It's fine.
Yeah, since randomly happens. What I did. Okay, so at the time you can see diffusion models here is a climber, and the king is still Gans. But then after 3 years, I think the order reversed. So you have diffusion and the auto-regressive model here. It's definitely the top, and maybe GAN is becoming a new challenger here. But I want to discuss is something hiding in the background. So it's no one noticed, it's very far away. So, but I think actually normalizing, this is something called normalizing flows, but actually has a very strong connection to this kind of diffusion-based models. So why is it? So if you look at diffusion model, it looks like what is our diffusion flow matching-based models, where it's basically you define forward paths where you have adding noise on images, and you learn a model to reverse that, right? Each step by step. I mean, in reality, it's not like this, but in this, you can think about that, like something like that. But instead of, so you know, basically each step, every time step, you know the distribution of how it looks like, the noisy images. But in normalizing flows, we try to learn a function if we can directly mapping images to any arbitrary noise. And then if the function itself is invertible, then you can just get a generative model instantly by randomly sample a noise and reverse that to get an image. So in this case, it's also trying to defining a distribution to distribution mapping. All the dimensions are the same from the input or output. But in this case, we don't care about what's the intermediate things. We just want to learn some kind of invertible functions to mapping that wrong. And this is the flow part. So what is the normalizing part? So the normalizing thing is basically this equation only. So it's called the chain of variable formula, which defines the density difference between the prior distribution where you sample from, like maybe the Gaussian noise distribution, and there's another term is I usually call it a local volume change, or it's also a determinant of the Jacobian. So this basically describes how the volume, the data space changes before and after you're doing the transformation. So because we can analytically write down their density functions, so we can just train them with maximum likelihood. And this likelihood term, you can write down the equation looks like this. So this is the same loss function what we usually train for language models. And you also notice that this loss function looks like a recursion, right? So you can recursively reply a lot of these kind of f functions from f1 to ft, and each one you can write down their log algorithm, and you can add them together. You can still write down the total log likelihood, and you can train them end to end. And in this case, you can see from top, top to bottom, the difference between the diffusion and the normalizing flows. Using normalizing flow, you can also have multiple iterations, not have to be like single iteration, and each iteration defines some transformations. The difference is, in this case, you don't care about you don't have some restriction what will be looks like in the middle. It's like a learning end to end, directly learning the path from the data distribution to noise distributions. So you don't need to define the underlying structure. So I also recommend reading some. There's a very nice survey at 2019 about normalized flow as state art. And also my colleague Laurent was actually pioneering on this direction and gave a talk at ICLEAR 2020 at the time, introducing the earlier works about these kind of ideas. I cannot find the exact video, but you can actually look at this. I will share the slide later. So yeah, Laurent's photo. So, but then the question is, actually, when I enter Apple, when I check our new papers, people usually ask two questions. Like first, I never heard of it. And second is this a special case of flow matching? So I think for people, maybe students join maybe recent years, may have the same feelings and also ask the ChatGPT about how many papers we have submitted to CVPR, accepted in CVPR, compared to diffusion and the flow matching base. It's basically only like 3 papers using techniques of traditional normalizing flows, but 300 papers using like flow matching or diffusion models. So why the case? I think the main reason is it simply does not work. So you can see that at 2019, the state of the art of images, it just looks like very tiny, small images. It looks great at the time because everything does not work. But then suddenly all the things getting working with diffusion, all the things scaling up and have scalable models, then you can see all the good change, all the work changes. And for the normal thing flows, there are 2 key problems. The first, because we need a directly learn an invertible function, and that one is itself gives you a strong constraint what you can learn. And second is you also need to compute this log Jacobian term in your loss function and take grading over that. And that one is also a not easy task. And because of the first and second, it just makes this kind of model very hard to scale up. And there's also other small problems, like a training stability, something like that. But what I tell you, actually, we can already scaling these models, doing quite well images, like getting very good images, or even better like text image generations, just like a state-of-the-art stable diffusion, something like that. So this is the major message I want to present this today's talk is normalizing flows actually can work better than you might think and can be a potential approach which people can use like getting close to diffusion models. And this covers 2 papers. The first one is we accepted ICML oral paper led by Shuangfei, is normalizing flows of capable generative models. And also another paper is we call it star flow, which is led by myself doing this kind of scaling latent normalizing flows for high resolution image synthesis. Yeah, so I'm on both work papers, but the first one is really good. So basically the key idea is to marry the diffusion to autoregressive. I will continue something like that. So we can think about what's the autoregressive, discrete autoregressive models. Is like each step you condition on previous hidden steps, and you create the next one using multimodal distribution. But we can also write down a continuous autoregressive model where each step is a Gaussian distribution. So you can write down this equation, and x means each step you given all the history, you predict the mean and the variance. And this function, because it's element-wise, you can simply reverse that to get a z from x. So it means that this simple autoregressive Gaussian function itself is invertible, and that becomes something called autoregressive flow. So the autoregressive flow is just a special case of normalizing flow. It defines that's the mapping from z to x and x to z using this autoregressive functions. And then these 3 problems suddenly disappear. The first is because it's autoregressive, I mean, I already showed that it's invertible, the invertibility is trivial. And second is because it has a triangle mask, so you can compute the log Jacobian very easy. It's just each step you predict the mean and have the log over that. So that is the only thing you need. And because of the first and second, now we can really see how we can scaling up these models. So, but unfortunately, there's a single problem is not solved is because single autoregressive flow is not powerful. As I mentioned, it's just a Gaussian distribution, right? Each step predicts the mean of variance. But in reality, our real life is not Gaussian. So you cannot using the Gaussian model to approximate everything. But because I mentioned that you can actually stacking a lot of flow blocks to keep the invertibilities. So essentially we can do is stacking a sequence of autoregressive blocks and then put them together. And then you can have a model and you can train them end to end, still loss get the same functions. So to recap, you can see here, on the top is the diffusion model. This is normalized flows. And the autoregressive flow, it just means that each block itself is an autoregressive model. And then it's like a combining both of the best friends. So in diffusion models, usually you need to have like a tens of thousands NFVs. Do we also really need this so many iterations? Because you can think about autoregressive model itself is very slow, but then you want to do hundreds of autoregressive models. But unfortunately, it's not the case. So in our new paper, we're showing that actually you only need actually 2 to 3 blocks to stacking together, and we can show that it's already a universal approximator for any continuous density functions. So there's a very simple toy example. Here you can think about you have 2 autoregressive blocks, but running in opposite directions. So on the top is like a right to left, and in the bottom is left to right. And if you write down the equations, and then eventually you can find that the Pxi given x smaller than I itself, it becomes infinite Gaussian mixture models, where you need to marginalize all the future latent variables to get it computed. And this just to be able to approximate any continuous functions. And this kind of future things is something like a hidden information that the model may be able to work. And in practice, because we're showing that we can have this, we're showing the university of this kind of multiple autoregressive blocks. And then second thing is we can just make it modernized. So most of the normalizing flow literatures, as I mentioned, because it disappeared at around 2020, but transformers is just literally taking off at the time. So then no one just really using transformers. So it's a simple quick thing is like we doing the similar analogy from UNet to DIT. We can just do a transformer version of these kind of autoregressive flows. And that's resulting to our new paper. That paper is called the TAR flow, which is simply taking autoregressive flow and implementing a transformer version. The third question we want to solve is we know the pure backbone should be a transformer. So what's the best architectures we want to use? So do we just have all these like autoregressive transformer, like take a llama and then just stacking them multiple times, which still sounds very crazy because you think about each llama block is so big, so deep. But in our case, actually, we're doing some small additional inspections. So we look at what it looks like in the middle generations. You can see there's actually a dramatic information change at the second block. So you can see that in the first block, it's just a noise, second block noise, third block, suddenly you get a dog. And then you generate dog and you continue over that. So this kind of information change is very different what you can see from diffusion models, where you first have low frequency information, the high frequency information, and because that is defined by the underlying the path, right? But in our case, because everything was end to end, the model find that is the best way to generate images. So you first directly generate some content. So we think we should promote this way because we should let the model to directly model everything based on the own purpose. So that makes us to derive something called a deep shadow architectures, where you have a very deep top block, autoregressive block on the top, and followed by so many small shadow autoregressive block. So the deep block is trying to handle most of the semantic informations, where whether it's class condition or text condition to generate the main contents. But the shadow block is make sure the whole thing is formalized mixture Gaussian thing I proved just now, so that it can be universal. It can be universal and can approximate any continuous distributions. So we also showing some empirical numbers that using have a deep shadow growth will improve the performance as well, and being a much faster architecture. And this thing is also have additional benefits. When you're doing have these kind of deep shadow architectures, we because I mentioned just now, deep blind will basically handling the semantics. We only need to just using we can only have the condition in the deep block. And in this case, the shadow block will looks like just some tokenizers. You can think about that. It's like a tokenize the very complex continuous distribution to something like a Gaussian-like, and the deep block will be running over that to predict one after another. And this also unlock a good, like a lot of possibility of using these models for modern development. For example, you can just replacing this deep block with any pre-trained VLM or LLMs, and fine-tuning continue on that. And that makes, I think, this kind of architecture is really useful in the modern cases. And moving forward, of course, we have stable diffusion LDMs, right? So normal learning flows should also doing something like that. So it's a similar analogy between from DDPM or LDM. And we can doing the same thing where you have a deep shadow architectures, but running everything in the latent space. This latent space naturally give you a much smaller space you can working on, and you can just make it possible to train large images. And also, there's another additional benefit. When you're doing this kind of mapping the real images with continuous space, that space is more have a more compact, and it's actually will further boosting the not only that just get a smaller space, but also boost the performance and increasing the training stability as well. So this resulting the final architecture looks like where we call it the star flow, where on the which is the first version is star flow, and then it's a star flow, and it's basically it's have a deep shadow share rating. On the left is the sampling approach, where you first given a prompt, you first sample a sequence of noise, and then you running the deeper autoregressive block from left to right to predict the first layer of X, and then using that one as an input and to predict second layer and third layer and multiple times. And after that, you take the outputs and send it to the decoder, which was used in stable diffusion. And the training is just a reverse of that, where you first have encoding, and then you're doing the from top to bottom. So if you just believe my words, but you just try on that, possibly you will get something like this. Unfortunately, if you're just doing the same thing, it won't work directly, because you can see a very weird loss, like exploding, and you'll have very bad garbage samples. So there's still something missing. The amazing part is the loss function itself. So maximum likelihood loss is very good thing for discrete space like language models, but it's actually a poison for continuous space, because in this case, where I mentioned just now, the second term is actually the local volume change. It's just a change, but I didn't define what's the original volume of the data point. So if in reality, real images like images or videos, they are actually lying on a very, very, very small, like a low dimensional manifold. So their volume is near zero. They don't have any volumes. And then if you multiply thousands on zero, it's still zero. So the model can just cheating on that by increasing this volume change, but you still have like a single tiny point-to-point mapping by training these models. And that one first will increasing the loss and make it very, very unstable. And second is in the sampling time, you cannot sample a good point to get the new thing. So it's like a very severe training test mismatch. So that's itself means that normal flow is not good. So this basically is a fundamental limitation of MLE loss for high dimensional space. But one thing, there's a simple solution for that, is we can add a small fixed amount of noise over the data point. Something like an image, you can add in a small Gaussian noise over that to increase its volume. Not in this case, each image itself is not a single point, but it's a ball over in the high dimensional space. So you can also think about it's just running a kernel over the data, smoothing out the space. And in this case, the model is very hard to cheat because if you make the volume change large, then you quickly get out of the prior distribution, and then you cannot, the prior distribution part will have a very strong penalty over that, so that you will make sure you won't have a very strong volume change. And in the case, you can have a good sample, like a better training test better training alignment as well. And that is also the key of how these kind of new things make it work compared to all the previous normalized flows. Usually people have do something called dequantization, which you have a very small, tiny uniform noise on the pixels. But in our case, we find that if you want to really increasing the visual qualities, we need to have a much bigger Gaussian noise. And that also gives us additional challenge, like if you're always learning over the Gaussian noise data space, then how can we get clean data? So the first paper we showing that is actually we can do something called a score-based denoising, because in the previous paper we can already write down their log likelihood. So we can basically follow the gradient over the log likelihood and to do one-step single denoising to given, if you model, first you sample the noisy images and then you follow the score direction, you can get a clean image directly from that. So that's just a give you, you're only adding a little bit test time compute if you want to generate a clean images from that. A second option is we can just leave all the things to the decoder. So if we're training everything in the latent space, like the LDN things, we can just, the decoder itself can just help you to denoise all any latent noise you have that. So in this case, in our second paper, we're just showing that we can actually do this kind of joint optimization, where you first you're adding noise over the latent in the encoder, and then you fine tuning both the decoder to denoise that latent, and also you train the flow on that. So here we're showing some results. The first one image is how generated latent, and second image is the noise latent, and how the noisy latent looks like if you decode it, and third one is the decode itself, how it cleans it up. And the final piece is guidance. So another very key successful things what diffusion model makes it work so well is they have this additional technique called classifier-free guidance. And this has been proved so influential for all the image generation or video generation models, not only diffusion, but also in autoregressive models. So can we do the same trick to autograph models? I mean, the answer naively is yes. So you can also do something like a naively CFG trick over this kind of mean and the variance. And it works quite well for the pixel space. But unfortunately, it does not work well for the latent flows. So I skip a lot of details, but if you look at this, in the latent space, if you're just doing this naive CFG, you will quickly get a very bad generated images. The main reason is because when we are doing this kind of the CFG in the flow space, we have separately doing the guidance over the mean and the variance. This is very different from the diffusion model where you only have one value, it's like it's just the mean. Here we have two values predict, it's the mean and variance. So in our new paper, we're showing that we can actually rederive this guidance equation from the score perspective, and then we have this something like this. It's a bit hard to read, but you can think about just in this case, this the mean and the variance, they are not independent anymore. They are dependent to be guided. And in this case, you can have much better image generation. It's close to real diffusion model looking like. So we have all the pieces from the main mass formulation. We improve the backbone, architecture, learning, and inference techniques. Basically, every pieces you can find some similar things from the diffusion and the autographic literatures, and these kind of actually modern things make these kind of architect models really working so well. And we're showing that the same thing we can also apply to normalized flows and make it work. And then you can just train this model safely on bigger data set and higher resolution images. So I also like to show some, inspired by signing yesterday, I can show some slides of implementation. It's basically just like how you do in a language model. We're stacking over multiple autographic flow blocks. And the only difference is in inference time, you reverse the order. You first generate from the deep block, and then you have the shallow block. So let's quickly go over the results a little quickly. So using this autograduate flow, first we can get state-of-the-art likelihood estimation. So although this kind of eclectic estimation is not really, maybe not a meaningful metric in many senses, but that's here we are just showing that we can actually using normal float to break the 3.0 number on ImageNet 64x64. We're showing that good results on ImageNet pixel space generation, but also more importantly, we can also do very good image generation on the latent space. Here we're showing the comparison between this our model with the existing methods. We can basically getting the DIT level as well. Here I put an image of DIT. You can see from left to right. I feel they are actually roughly similar quality, especially compared to the 2019 images. And more importantly, you can see that if we're doing an apple-to-apple comparison where we have all the same parameters, architectures, compared to the training curve between the staff row and also autoregressive DITs, we can see clear our model converges much faster than both architectures, both methods, and also give a better results, because in this case, we are directly learning on a continuous space, but in all the pure autoregressive model, which is based on discrete space, they may have quantization errors. And we also show the scalability where you can just safely increasing the model size, you can give you much lower and lower loss, also get a better image generation qualities. And this, combining all these pieces, we can get this kind of, make this quite well for text image generations, giving different prompts. And the one thing I like this model is it's also unlocked a lot of interesting applications. For example, image editing, where you can simply take these two autoregressive flows, concat them together and preparing data like a text, image. You let the model just train one model directly for that. So you can supporting image editing. It can also support interactive image editing, which means that you first generate a first image, and then you don't need to read that image again because all the information was saved in the KV cache. And you can, as a condition, you will generate a second image based on the new editings. And you can keep going doing this if you have the training data for that. So summary, this is a small table I could compared with the autoregressive compares diffusion model, autoregressive model, and autoregressive model with diffusion head and the pros and cons. But the real thing is, I really think this kind of spark new directions where we are not like stuck in one or two other architectures, but maybe we can find something the best of both worlds, or keep exploring the new direction of models development. So I want to discuss some future directions because this is a relatively very new model. It's basically 2 hour papers, but I already see there's some following up. For example, this autoregressive flow is extremely slow because it's autoregressive and it has multiple autoregressive. But there's many people have been trying to speed up. For example, you can doing something like speculative decoding, or you can also do distillation over to make it not aggressive. And another thing bothers me a lot is the noise. So although I mentioned that that is actually the key to make these things work from not working to working, but how can we really learning something noise-free training? Or maybe you can have some smart learnable noise, which makes sure you don't, when you're adding noise to the data, you don't want to destroy the important informations. And more importantly, maybe you can extending this model to more modalities, like we can train images, video, 3D, and actually we can using this model to achieve the real multimodal generation, like a text image in, text image out, like Jiaming mentioned. Here are some like a preliminary attempt. We can also train video model on that. So finally, do you think this kind of models compared to the standard autoregressive models, we can maybe there's a one step towards make a real world model which can be useful for embodied or something like tasks. So this is my vision. Goal is maybe there's additional new thing. We can move the normal flow again back to this climber, and hope people can help to moving that towards these directions. And thank you so much. I will thank the amazing team at the Apple MLR. We are actually very bottom-up blue sky research lab. I've been there for many years. It's a great place. And also there we have the paper and the code for the first paper. And the second paper, the code will be coming out soon. So I'm happy to take any question offline. Yeah, sorry.
Okay. Thanks, Jiatao, for the very great talk. Actually, like, once TarFlow is out, Jiaming is mentioning to me like this might be the next game changer, in generative modeling. Oh, sorry. Can you like share it again? It's the presentation.
Hi everyone, I'm Varun Jampani from Stability AI. Yeah, thanks to organizers for giving me this great opportunity to talk in front of you and organizing this wonderful workshop. So today I will be talking about more on the practical applications of diffusion models, not more on the theoretical side, but more on the practical applications of diffusion models, where I will talk about some of our works on lightweight and heavy adaptations of diffusion models for various complex vision tasks. So specifically, I will be talking about three different directions. One is on this material control and transfer, and second one is on novel view synthesis, and third one is on 4D generation. First is on material transfer and control. So last year CVPR, we presented this work called Alchemist Parametric Control of Material Properties with diffusion models, where we showed that like stable diffusion can be fine-tuned for very precise material control in images. With very simple fine-tuning, we can show stable diffusion can be converted into a very, very powerful material translator here. So we can actually precisely control transparency, roughness, metallicness, albedo, etc. So here to actually adapt stable diffusion, we just have to create some small synthetic data set with 100 objects, 1200 materials, 400 HDRI maps. And based on that, we actually add a slider to stable diffusion that also takes this small slider that -1 to 1 that actually explicitly that implicitly changes the material properties. I mean, if you solve this problem in an explicit way, we have to estimate 3D material properties, VRDF, etc., which is actually quite complex problem, but this can be implicitly tackled using modern generative networks, diffusion models with some simple fine-tuning. Following that, we proposed this work called JEST, Zero Shot Material Transfer from a single image. We presented this at ECCV, where we showed that like we don't even need to do fine-tuning to do some material task with stable diffusion. I mean, stable diffusion out of the box already works on some material transfer applications. Here the task we tackle is that like given an input image and a material exemplar like this, and we showed that like stable diffusion can be used out of the box to transfer these materials onto that input image to some extent. I mean, this is not perfect results, but it works surprisingly well out of the box. I won't go into too many details of the architecture here, but it's a mostly very simple or standard IP adapters, control nets, and in painting, diffusion in painting. So we actually pass this material exemplar to this clip image encoder and inject those knowledge into diffusion in painting, like in IP adapter. And from the input image, we extract depth map, and we use the depth control net as a geometry guidance. And also we automatically get the foreground segmentation marks. And with this simple in-painting technique, we can already transfer these materials onto this target input image. And these are some sample results. For each of the result, we have this material example and input, and you can see it transfers reasonably well those material properties to these different types of objects and different types of materials. And there are some comparisons with baselines and Dream Booth, IP adapter, and etc. And we found that our simple technique works quite decent as well. And we can also run this multiple times for different objects in the scene. So we can also transfer materials to multiple objects in an image. So just to briefly summarize, that's a very quick overview of this work. To briefly summarize, we found that like stable diffusion with IP adapter and control nets and in painting directly works out of the box for material transfer, works quite decent. And it bypasses the complex task of explicit 3D shape and material estimation. But still, everything is done implicitly. We don't have an explicit control over different material aspects like base color, specularity, roughness, etc. And in the follow-up work, we try to address some of these. In this follow-up work, which we call Marble, material recomposition and blending in clip space, which we are going to present in this year's CVPR. We try to have a more precise control in this stable diffusion material control, but while still only working in clip space. So far, I've shown two types of work. This Alchemist, where we have the precise control over material properties, and Ingest, where we can transfer materials from one exemplar image to another. So in this work, we ask the question, can we perform a series of material controls and transfer on diffusion models by only manipulating the clip space? So why only manipulate clip space? Because such real-world data sets are difficult to obtain. So we have to rely on synthetic data sets to train these models. And we don't want to lose the generalization capabilities of stable diffusion. So we want to adapt these models only on synthetic data sets. So we are questioning how much we can manipulate just the clip space that goes as an input to the stable diffusion to actually manipulate the materials here. So we have some interesting insights here. So one insight is that like, instead of injecting these clip space features into all blocks in stable diffusion, we can actually, there are certain blocks in stable diffusion that are more suitable for material transfer. So by selectively injecting these clip features into certain blocks in stable diffusion, we can get much better material transfer while preserving the structure from original input image, as you can see on the right side results here. And also we find that like we can actually freely interpolate these clip features. We can actually compute clip features on the left material exemplar and also the right material exemplar. And we can actually interpolate in the clip feature space and inject those clip features into stable diffusion. And we can get also this translation in the output material transfer thing. So it's kind of like a clip features has a good arithmetic happening in this material transfer. So we actually use this property to actually learn how to precisely control different material properties in the output image. So more details, I won't go into too many details here, but in general, at a very high level, we attach a small MLP on top of clip, P theta, that also takes a delta that how much, let's say this P theta is for like, let's say transparency. And it also takes a delta saying how much to change the transparency. And this P theta modifies these clip features. This moves this clip feature in such a way that it will make this pumpkin more transparent or less transparent or more rough, less rough, etc. kind of thing. And we train this with simple MLP. Since it's an MLP, it does not require much data to train. So we actually generate some small synthetic data set where with this varying roughness, transparency, metallic, glow, etc. And we train these MLPs on top of clip features that can actually be injected into stable diffusion to actually precisely control these material properties. These are some of the example results. On the left, we see the context image and the material exemplar below that. And in addition to transfer the materials, we can also precisely control different attributes here, right? Roughness, metallic, transparency, glow, etc. And we can also do multiple controls at once. We can invoke multiple MLPs that are related to roughness or metallic. For a given material, for a given input image, we can increase roughness and decrease metallic, and also with this transparency, etc. And one of the nice things by not fine-tuning Stable Diffusion, by keeping it intact, is that we are not losing its generalization capabilities. So it can still generalize to non-trivial images like artistic images. For instance, we can still change the transparency of Van Gogh painting, actually. So we can take this teapot in the style of Van Gogh, and we can actually increase or decrease the transparency. So these MLPs that are learned on synthetic data sets generalizes quite decent to these artistic style images, like these graphic style images in the bottom or this Van Gogh style images on the top. It's kind of quite interesting. You can see that it is somehow doing these transparency changes that make sense, visually makes sense, even though it is not clear what does it mean to be transparent in this. Just a quick summary of Marble. We propose a material transfer and we propose a way for material transfer and control in diffusion models, where we can control over different material aspects, metallic, specularity, roughness, etc. And it operates only in the clip space, so that it generalizes to various style of images. And in the future, we would like to go beyond images. This implicitly done on the images, but we want to go beyond images on videos and also into 3D as well. So that is the first part of the talk, and the next part I will briefly talk about this recent work on novel view synthesis called Stable Virtual Camera, where we actually adapt diffusion models for novel view synthesis. So precisely this is the task. So given a single input image or a few images of a static scene and a very precise 3D camera movements in a space, and it also takes precise camera intrinsics like focal length, etc. And this video model takes this Stable Diffusion, this adapted Stable Diffusion model takes this input image or a few input images and this precise 3D camera, and then actually generates these videos following that camera path. So in this one, we actually propose a single model that has high generation capacity. It can actually generate even 1,000 frames. If you want, and it has very good interpolation smoothness. It can actually create quite good interpolation between different images that are given as input. And it's also quite versatile to many types of NVS tasks, novel view synthesis tasks. It can take single image, 2 images, few images, and it can also be, images can be quite far apart or close by each other. And here again, we adapt Stable Diffusion model into a multi-view diffusion model. And we adapt Stable Diffusion such that it can take M input images and N output images. And a bit more details. So we actually embed these camera paths into these Plucker embeddings, which is a spatial representation of camera matrices. And we add these adaptive layer normalization layers into these convolution layers, 2D convolution and 3D convolution layers into this unit of Stable Diffusion. And that way we can actually take these multiple input images and also multiple output images in the target camera angles. And to actually generate long camera paths, because in only single pass we can generate maybe 16 or 24 based on the size of GPU you have. And to actually generate long camera paths, we first generate these anchor frames, and then we interpolate between the anchor frames so that we can have a smooth video as an output. So with this procedure, 2-pass sampling, we're able to get some quite decent multi-view consistent outputs compared to some state-of-the-arts like Cat3D. We get actually quite good consistent videos in the output. Here's some of the results. So another key contribution of this work is that we also extensively benchmarked most of the existing works and also this work on a lot of benchmarks, so that this will serve as a a good baseline for also the future work as well. And there are some of the visual results. Given a single image, we can do all these different types of camera movements, predefined camera movements, like orbital, spiral, skate, dolly zoom out, etc. These are some of the single image NVS results. As you can see, the reflections on the lake are also looking quite good. Sorry for the videos here, yeah. And also from these sparse views, just given those 5 input images, we can also create some of these complex camera paths and move around the scene. And this is all a pure, completely video generated model, there is no explicit 3D at all here. These are all, you give 3D camera paths as input to the network, and this is a pure generative model. We want to push the limits of diffusion models on how far they can go here. And a glimpse into open world NVS, we can also capture a lot of images from an apartment or something, and then create paths like this. And our model can generate videos like this on the right from those input views. And we also have a model open source, and we also released a Hugging Face demo where we can actually precisely specify the 3D camera paths. So we show these intermediate point cloud representation, which we don't use as input to the network. This is just for an UI to precisely specify the 3D camera paths. And given such specification of 3D camera paths in this 3D space, and we can generate videos like this from our video model. Just from very few images. And these under comparison with prior works, Viewcrafter, Cat 3D, as you can see, we can generate quite decent and smooth results. And there's still several limitations, mostly because of the type and amount of data sets we use. It does not work that well on humans and animals, on dynamic textures, etc. Just to briefly summarize this work, we propose a single versatile novel view synthesis network that has high generation capacity with long video generation, and it has a good interpolation smoothness, and it is versatile in terms of input view conditioning and number of inputs and the size of outputs, etc. And we would like to, there are still several limitations in terms of the result quality. Yeah, feel free to play with the code and use it yourself. And we would like to generalize to more real world scenarios and dynamic scenes, etc. Next, I will cover some of the dynamic scene aspect here. Last part of the talk, I will briefly show our work on 4D generation, where we have a couple of works, stable video 4D 1.0 and 2.0. Especially, I will talk about this work, stable video 4D 2.0, where we enhance spatiotemporal consistency in multi-view diffusion models for high quality 4D generation. So here, this is the problem setting. In this previous work in stable virtual camera, we deal with static scenes where we take single image or a few images as input. And in this 4D generation, we deal with dynamic objects where the input is a single view video, and where the goal is from the single view video, this multi-view video generator also takes the camera angles, the 3D camera angles, and the goal is to generate how this video looks like from these multiple camera angles. Essentially, this is to create a spatio-temporal grid of images across different camera angles and across different time steps in these video frames. Okay. And given this spatio-temporal grid of images, and the goal is to optimize a 4D representation from it. So we had this earlier work called stable video 4D, which is accepted, which we presented at iClear 25. Where we adapted the stable diffusion model with view attention and frame attention layers. So given this reference video, we first generate reference multi-views for the first frame. And then we added these additional attention layers across views and across frames, these view attention layers and frame attention layers, to create this to generate coherent spatio-temporal grid of images. But it has some limitations since we first generate these multi-view reference multi-views. If one of the, let's say for this dinosaur, if one of the legs is missing in the input view, sometimes it also misses it in the output views here, because these reference multi-views may miss that leg. So it is not robust to self-occlusion in the first frame. It also often produces blurry results because of this disentangled attention across views and across frames. It is not completely spatio-temporal consistent, these novel views. So in the Stable Video 2.0, we propose several innovations on top of Stable Video 4D 1.0. Specifically, one key modification is that like we add this random masking on these reference multi-views so that the model is not completely reliant on these reference multi-views. So that with this random masking, we find Stable Video 4D 2.0, SV4D 2.0 is much more robust, resulting in much better results compared to first version. And in addition to these view attention and frame attentions, we add this 3D attention that can attend across views and time, both axes at the same time. So this will actually create more spatio-temporally consistent views that are consistent across both views and the time. So with this SV4, with this modification, we get much better high quality results that closely follows the input video appearance and stuff across these multiple views. And one of the hidden power behind this model is that like, because it is tough to get real world data sets on this 4D, so we actually completely train this model on synthetic data sets. So even though there exists a lot of synthetic data sets, there is a lot of issues with those synthetic data sets because they are manually created by people. And so we actually spend significant efforts also automatically filter out a lot of bad data from this based on bad lighting, minimal motion, etc., and inconsistent scaling, etc. So with this improved quality data by filtering out, even though we throw away more data and use less data here, so it's still better to use high quality data and we get higher quality results with SV4D 2.0. And last improvement we have for this with compared to SV4D is that like we also have a better nerf optimization on top. Given this multi-view videos from this SV4D 2.0, we still need to optimize this explicit dynamic nerf optimization to actually create these explicit 4D assets on top of this. So I won't go into the details here and all these nerf details in the interest of time. Please check the paper. And with this two-stage nerf optimization, we actually also get better 4D models on top of our previous works. So these are some of the novel view synthesis results. This is the input video, and these are novel views compared to novel videos. As you can see, SV4D 2.0 has much higher quality details preserved compared to other works, state-of-the-art works. And also this is another result where you can see the more details are preserved from the input video. Just from a single input video, we can create these 360 novel view videos. And these are some of the results on the real world video. Since we adapt stable video diffusion, it can also generalize well to real world videos, even though we fine tune using only synthetic data sets. As you can see, even from the real world videos, we can get the much higher quality details compared to state-of-the-art work here. And the result on the real world video, under one, as you can see, there are more fine-grained details preserved with SV4D 2.0. And you can actually place these cameras anywhere across this 360 angle. This is actually a dynamic nerf result. This is not a video result. On top of that, we optimize dynamic nerfs. These are explicit 4D assets. The compared to state-of-the-art works like stack 4D, L4GM, consistent 4D, we get much higher quality results here as well. Briefly summarize this part, we adapt video diffusion models for 4D generation, and we made several improvements for Stable Video 4D, our previous work, with improved data processing architecture and 4D optimization. And we're actually working towards generalizing to more real world scenarios, etc. To conclude my talk, we hopefully this convinced you that we can, you're already convinced, hopefully by the much of the works at CVPR, that we can adapt. Diffusion models are quite powerful and it can be adapted to quite range of tasks. And these are some of lightweight. I have given examples on the lightweight and heavy adaptations, and it can be effectively adapted to a range of complex vision tasks like material transfer control, novel view synthesis, 4D generation, and relighting, and a lot of interesting tasks. which are not traditional, which are traditionally quite complex tasks to handle. And in Outlook, we would like to do more controls and better generalization to real world settings. Yeah, thanks. That concludes my talks. Happy to take any questions. Thank you.
Yeah, so we have time for one question. So anyone, if you have a question, feel free to. Oh, sorry, I thought that's the question. Yeah. Okay. Oh, sure, please.
Yeah, the question there here is that like for the stable virtual camera, whether it works well for humans stuff. Right now, this version does not work well because of the type of data. It does not include much human data sets stuff. So, but we're actually trying to improve on it from different aspects.
Yeah, okay. So let's thank Varun again for the great talk. So next we'll have Arash from media to talk about what's wrong with
Thank you.
and this will just share your screen also.
Yeah, let me just make sure this is. Oh, that's nice. And can you just scroll the slides a little bit?
I like the next slide to see what it is.
What do you mean? It's on the other. What do you mean?
So can you just show the next slide so I can see you?
But it will spoil my next slide.
Oh, I see.
I'm joking.
Okay, sure. Yeah, it's great.
He was saying go to next slide. I said it's gonna spoil my next slide. I don't want to go to my next slide. Yeah, so this is a workshop on what's after diffusion. So I thought, okay, if you want to talk about what's after diffusion, we should talk about what's wrong with diffusion. Otherwise, why would we go to another framework if there was nothing wrong? I used to work on VAEs around 2019-20. My manager asked me to give a research proposal, and I said I want to work on energy-based models. And he said, why? I said, well, GANs have all these problems, and I want to solve them with energy-based models. And around that time, diffusion models came, and I realized diffusion models are just kind of energy-based models that are solving kind of all the problems that I was trying to solve. So I think now if you're thinking about what's after diffusion, I think we should think about what's wrong with diffusion to go towards that. So I've been using this slide for a while now. This is an image generated by DALL-E 3. I should say a few years ago, maybe 5 years ago, this was a dream for us. It was very hard to generate even images of CVPR10, yet alone this kind of complex scene where there are multiple characters, multiple objects interacting with each other. Diffusion models can generate avocados that go through midlife crisis and say, I feel so empty inside. And they talk to a psychiatrist in the shape of a spoon, which is so funny. So today, I want to, before talking about all the problems with diffusion models, I want to give them a bit of credit. So I want to start with why they're amazing, very quickly. And then later talk about 3 main things that I think we need to improve. One around sampling efficiency and also training efficiency. And then I want to talk about how diffusion models need to capture complex distribution and heavy tail better. So let's start with why diffusion models are good. So I want to keep this part brief. I think you're already convinced most likely diffusion models are good. Except if you're trying to build normalizing flows, which is also very good. Maybe we should do. I think there are 4 things that kind of
cool about diffusion models. They generate very high quality samples. They're extremely stable and scalable training objective, right? So no one really has any issue with regression loss. It's just really easy objective. You scale it up, you train it, and at the end you get a very good generative model. They have very nice coarse to fine inductive bias that works really well for images. That we know diffusion models start generating images from some low frequency content and gradually add detail. So this is really nice actually about diffusion. It gives kind of like a hierarchical structure in the spectral domain. And also you can have very good control and guidance, right? All this like classifier free guidance, everything you saw today, Varun was talking about, all amazing work on like how can we introduce camera condition, all other and or like lift it to 4D. This is really amazing. I want to just talk about like very briefly like this work that we've been looking into. We call them blobgen. We had blobgen 2D, we had blobgen 3D and blobgen video, and this is a work by our former intern, which will be presented this Sunday, and it's about I will show the video. It's about basically taking blobs as input and think of every blob as an object with description attached to it. So it describes what is the object inside it. And we think of diffusion model as kind of like a rendering module that will take these blobs and convert them to videos, right? In the three examples, I'm showing mostly blobs defined in 2D, but this example in the bottom right, these blobs actually are defined in 3D, and we define camera trajectory, and we project these 3D blobs to 2D, and we use this 2D video diffusion model to generate this video. And you can see how this this video here is 3D consistent, even though it's just 2D video generated, because blobs are consistent, this video also stays consistent. By the way, for 1 or 2 days, my videos stopped working, like Varun was having experience. I think some intern put some code to PowerPoint, so please revert. This is breaking my PowerPoint, so I don't know if there's some intern pushing some code or something. Anyway, so let's go to problems with diffusion models. I want to spend most of the time on sampling from diffusion models. Earlier, Jiaming was showing this trilemma, generative learning trilemma. We actually advocated this at the ICLR 2022 paper. We had flipped version of that. We had other way around. So we looked at generative models and we realized that there are 3 criteria that are very hard to sacrifice with existing generative models. These 3 criteria were fast sampling, mode coverage, and high quality sampling. We looked at GANs and we said, oh, GANs are very fast. They have very high quality samples, but they miss modes by definition. Like we know this issue about GANs. If you look at normalizing flows or VAEs, they are very fast at sample generation. They have very good mode coverage, but they struggle with generating high quality samples. And I should start changing this slide after seeing what the talk Jiatao gave on normalizing flows also being able to generate really good images now. And looking at diffusion models, we see that they generate very high quality samples. They have very good mode coverage, but we know that they're extremely slow to sample from. This was the time we said, let's call this generative learning trilemma. We could also come up with like Mickey Mouse of generative modeling, because this looks like kind of Mickey Mouse to me. We mission ourselves with accelerating diffusion models, right? If we could accelerate diffusion models, we would be able to address all these 3 criteria together. So when you think about accelerating diffusion models, you kind of need to think about 2 different directions. You either think about distilling SDEs, which kind of boils down to distilling distribution of samples, or you need to think about distilling ODEs, which usually translates to kind of distilling these trajectories, that there's like one-to-one correspondence that exists between noise and data. So I'm going to give you a bit of flavor of each one of these categories, like distribution distillation and trajectory distillation. When we were trying to look into the denoising process in the distribution distillation case, we noticed that when you're denoising, right, if you are at a particular diffusion step and you try to denoise for a smaller step, the normal denoising assumption is correct. But the moment you try to denoise for a very large step, this normal assumption breaks. Your denoising distribution ends up being highly multimodal. And we realize that that's actually a moment that you no longer can use very simple conditional model to generate less noisy version of data given noisy instance. So in our early work, we were trying to figure out what's a good denoising model where it will allow you to take large denoising steps. We honestly started with VAEs. We spent maybe like 5-6 months on VAEs. We couldn't make them work. And then we had a very good intern, and he started looking into this and said, let's use GANs, conditional GANs, see if we can learn a denoising GAN to take large denoising step. And very early on, we saw a very positive signal where like we could not train conditional GANs to take a noisy image and go back like over like a large denoising step and produce this less noisy version of my cat's picture, Peanut. I should say I've used this picture so many times that now so many people are using it. This is in public domain. Please use as much as you like. My cat's picture is now more famous than I am. He made it to Nobel Prize lecture by David Baker a couple of months ago. I'm very jealous of him, to be honest. So David Baker has this slide where like says like image contribution by Arash Vahdat, and that's my contribution to science. Peanut. Yeah, so speaking of distribution matching, we can also think about another framework called DMD that uses a very clever trick about reverse KL. So distribution matching distillation, or DMD, relies on reverse KL, which you can express in this form. Think of Q as your one-step student, one-step sample generator, and P as some pre-trained teacher. And in DMD, they basically use this reverse KL expression where it's basically expected value of this log-likely ratio under this student distribution. This is a bit hard to connect it to a score function, but the moment you think about the derivative of reverse KL with respect to parameters of this student, all of a sudden these two score functions appear, right? Now here we have, this is just reverse KL I showed in the previous slide. We have the score function for some real data or pre-trained teacher. You have a score function for fake data, which is the samples generated by one-step generator, and you have this gradient of the generator. So what this means, this basically means if you want to optimize reverse KL, all you need to do is to take the score function you have trained, the pre-trained score function, compute or approximate the score function of your fake data that comes from your one-step generator and backpropagate it to your generator. So this would look like something like this. Generator, one-step generator generates sample, and then we diffuse it. You can apply this expression on different diffusion steps. So you can diffuse it and then compute the real score, and you also approximate the fake score on generated instances, and you take the difference and backpropagate. If this reminds you of GANs, these are kind of fancy GANs. You can think of this side as generator and this side as a discriminator that has been designed in a very clever way. So it's not very, very different than training GANs. So when we think about this, we were like, oh, but they're using reverse KL, and reverse KL, we know that it's highly mode-seeking. Like, so if you're thinking about applications where quality matters a lot, maybe mode-seeking behavior is okay. But in some cases, we may not want to sacrifice the diversity in the data. So we asked ourselves, is there a way we could generalize DMD to other divergences? And looking back, there's this known divergence that was also heavily used in GAN literature called F divergence. F divergence is also similar to KL divergence, is expressed as expectation with respect to skew, where you're computing expectation of this F function that takes, it's a scalar function that takes the likelihood ratio as input. And the only requirement for F is that it should be convex so that this D is a valid divergence. And the statistics community has built like many different, there are many different forms of these F divergence, and they come with different flavors. Some of them are mode-seeking, some of them are a little bit mode-seeking, and some of them are not. If you use them for training these models, some of them have like saturated gradients, some of them don't. And then if you look at the variance of gradients, some of them have low variance, some of them have high variance. So this kind of generalization allows us to basically go beyond just reverse KL and consider other divergence. And in our experiments, we saw that actually Jensen-Shannon divergence that used to be used a lot in GAN literature also really works better in many experiments compared to DMD-based or reverse KL-based approach. I should say the expression for the training now admits this new weighting function in front of the previous term you saw. And you can think of this weighting function. It's a very simple weighting function that depends on the likelihood ratio. So you can think of, like, for example, if you generate a sample where it has high likelihood under the real data, but low likelihood under the generator, this sample will get very high weight so that we match basically the fake score and the real score better for that sample, right? So it kind of reweights the DMD loss based on the likelihood ratio of that sample. Yeah, these are some of the instances created by FDistill when we applied it to SDXL. Yeah, so I talked about distribution distillation. So I want to talk also about trajectory distillation-based approach, or something like consistency models. So recall that for when you're sampling using OD-based approaches, usually you have these deterministic trajectories that start from noise and end at a particular data point, right? The basic idea of consistency distillation is to introduce a consistency function that we're going to denote by F here. And the consistency function's objective is to map all the points on one trajectory to the same data point. So all these Fs on this trajectory are supposed to produce the same x0 for all the points on the OD trajectory that ends at x0. Consistent distillation uses a very simple objective where you evaluate F at some like xt, some diffuse training data point, and you also evaluate F by following, let's say, OD trajectory towards like higher noise levels. And this consistent model basically tries to minimize the difference between F evaluated at a smaller step compared to F evaluated at the higher noise level, right? And it applies some like stop gradient on this smaller time step. The basic idea is that F by design at 0 is identity. So it's just for Fx00, it just returns x0. So by design, this F learns to denoise or predict x0 for smaller steps and gradually transfers this knowledge to higher and higher noise levels, such that eventually we can take this like instance at very large steps and predict x0 using this consistency model. When we looked at consistency models, we noticed that there's something interesting happening with these models. At the small time steps, these models need to do denoising, and at high noise levels, they need to do generation, right? So input is almost purely noise. And when we look at the training dynamics, we set it for a smaller step. So these are like small time steps. And this is the FID during training, or denoising FID during training. We noticed that denoising FID gradually goes up as we're training these models for consistent models. But the denoising FID for higher steps continues going down. So we realized that what's happening is that the model needs to trade off between denoising at low steps and denoising at higher steps. But what we care at the end is denoising at higher steps. We don't care that much about denoising at the low steps. So what we came up with, we said, can we do some form of like truncation in time? So let's first train consistent models at the full diffusion spectrum. And then after some time, we stop training and we use the denoiser, for example, train up to this time step t, and use that for training the consistency model at the rest of the interval, at the like from this t prime to capital T. This comes with a bit of challenge because you need to now handle the boundary condition here, because now you need to come up with a boundary condition that satisfies the requirement for consistency function. But we came up with a simple parameterization that handles that. And we started using this technique now. Not only as you're training these models, your FID will go down, but even it avoids some instabilities that we had seen with consistent models, for example, on ImageNet, where training would blow up if you keep training this model. Yeah, so this was basically two different works we had done on either distribution distillation or kind of like diffusion trajectory distillation. Thinking about going back, like thinking about high level, if we want to think about complexity of trajectories, so these are like some OD trajectories that are generated for this toy data set, starting from noise, going to this like one-dimensional toy data. If you think about these curvatures, right, these are the problem that happens when you want to accelerate these models. These curvatures introduce discretization error, and that's where we need to go slow, like when we're simulating these ODs. So if you want to make these trajectories smooth, like if you want to make them straight line, you have basically two choices. Sorry, I should say that these curvatures are function of score function, right? The score function that we're training. And the score function is for every training data and forward process, it's fixed. So if you want to change the trajectories or if you want to change the score function, you have basically two choices. Either you need to change the data distribution or you need to change the forward process, right? So because these two are the things that define the curvature, basically. So we ask ourselves, okay, what's a good forward process for videos, right? So for videos, what we've seen, my videos are not playing very well. So for videos, usually we use the left side. Left side, we have this independent Gaussian noise that is injected and is used for diffusing. But there is some recent work that argues you can use warp noise, right? So I don't know if you can, I mean, if you stare a lot on that noise, you see there's something like moving in that warp noise. So this can be generated assuming that you have some input video or you know the motion in the video you want to generate, right? So there's a series of work that argues, I want to show the video again, argues that you can actually use this warp noise to train video diffusion models. And in recent work, we call it EQVDM or equivalent video diffusion. We analyze this. We analyze what would happen if you use warp noise for training video diffusion models. One thing that happens, remember that noise was moving for that train, right? So what we want in this video diffusion model, we want the output to basically be transformed following that motion. Right? This is kind of like you can think about like now you're expecting your video model to be equivariant with respect to transformations in the input. So we actually showed in the paper that if you use warp noise for training video diffusion models with just a very standard denoising loss, what you're doing, you're actually training your model to be equivariant. You're training your denoising model to be equivariant with respect to input transformations. So this is extremely nice because now if you have applications like let's say video to video diffusion, where you know that there is a content is being moved with a particular motion, your model is guaranteed to generate output that follows the same motion, right? And this is done by just training, by the training objective. This is basically just equivalence idea. If you warp the noise following a particular, for example, optical flow, your denoiser, the output of the denoising model will also follow the same transformation. And this is really nice because we're achieving this only by training. We're not introducing any regularization. We're not introducing any additional module into the training, and we're not doing any like guidance or anything to get this equivariance with respect to input transformations. We only, like previous slide, I was talking about warping following optical flow, but you can be even clever about this. You can say, how about I stitch noise to 3D meshes? We used to use codename sticky noise, meaning that we would stick the noise to meshes, but you can now render these noise at different orientation. Right? You can start like rotating this object and render them, and you get this like Gaussian noise kind of stuck to the pixels. And if your underlying video model is equivariant, if you apply that video model to something like this, it will generate now 3D consistent output. Now you see like you can kind of train 2D video models, make your noise 3D consistent, and hopefully you will see that the video that is being generated is also 3D consistent using this. Last thing that was a bit surprising for us, we never thought about sampling acceleration. At some point, Chieh, the first author of this paper, he ran some experiment. He said, I want to reduce number of steps to see if the performance will be the same. So this is some, I think, indoor static scene generation videos, where we saw that as we reduce the number of steps, the FID stays actually very low until the very end when like we reduce the number of steps below 10. This was very surprising for us. Basically, using now warp noise, you can even reduce the number of steps. So that was kind of interesting, like, so being able to design some new forward process specifically for video models. But what about changing now data distribution to make these trajectories that appear in diffusion models smoother? Simplest technique that you can use is probably variable autoencoders, right? Originally, when we proposed latent score-based models, this was actually before latent diffusion models. We proposed this end-to-end training objective where we were training VAEs to bring the distribution of data close to normal, and we were training diffusion models on the latent space. And our idea was that if latent distribution is close to normal, it's going to be very easy to generate it. It's going to, the trajectories in the latent space will be smooth. We indeed actually showed some empirical result that trajectories are very smooth, such that you can just reduce number of steps in the latent space and get very good samples. This kind of latent design come with some other advantages, such as you can now apply to discrete data, you can apply to graphs or text and this kind of things as well. But I was just in another workshop yesterday, and I said it's kind of funny that it's 2025, and we still don't know what's a good latent space for latent diffusion models. In my paper, we proposed to use VAEs, but then Robin later in his latent diffusion models, he took a very different approach where he was advocating compression. He basically wanted to train autoencoders that would go to very compressed space. And then in that compressed space, he was arguing it's easier to train diffusion models. There is some recent work that Robin also mentioned earlier this morning that maybe we need equivariance in the autoencoder. So if your input of encoder moves, maybe your output of encoder should also shift or scale in an equivariant way. And there's some evidence showing that these autoencoders also allow, for example, faster training as well. And now there's also another line of work that is kind of looking into how can we inject additional features or representation into the VAE encoder, right? So rather than just using convolutional network to go to compacted space, can we make this space semantically meaningful? Is there a way, rather than gathering, pixels based on the RGB values in one space, can we gather data based on some semantic meaning in the latent space together? I think this is a really good open question, and I'm a bit surprised that even like until now, we really don't know what's a good latent space that would allow better or easier training of diffusion models. This brings me to a third part, and which will be much shorter, hopefully. So I'm going to talk about a little bit about training efficiency. So let's think about what happens during training of diffusion models, right? So let's think like we are standing on this XT, and this XT is passed to denoiser. Every time we're training denoiser, we say, okay, there's this X0, I diffuse, I got this to XT. Now I'm gonna train my denoiser to predict this blue dot here. Then another instance comes and says, okay, now we sample from this mode. We got to this XT. I'm gonna train the denoiser to predict this X, right, to point towards this. And then another sample comes from this mode, and I diffuse, I get here, and I tell denoiser, you know what, now you need to predict this. So if denoiser had the math, would say, what the heck, what do you want me to do? Like one time you say predict this one time you say predict this one, and I say, well, you're supposed to predict the average, right? So this is a very mean objective. Like you're never giving the model what it's supposed to predict. Every time you're giving different output, and you say, by the way, you need to learn how to average. So I think this is one of the problems why training diffusion models is extremely slow, because this is extremely high variance objective. That's why you see in literature, you need very high batch size, and you need large training, and you need to use EMA, for example, right? I think this is maybe one of the reasons why REPA is very popular. Now, I saw so many speakers this morning talking about this. REPA is kind of doing something interesting. So think about like you have this now high variance objective, and diffusion model is struggling to learn good representation, internal representation, because of the high variance. And we come and we say, you know what, you can use dino features if you need. And you can think of this dino feature distillation or alignment, some form of, giving another objective to the denoiser so that it learns some better representation, such that it can do this denoising job maybe a bit easier, right? So you can think of this alignment maybe as a variance reduction approach to at least allow the denoising model to learn some useful representation for learning the denoising, right? So I think there is this need to understand how can we reduce the variance, how can we maybe make the job of the denoiser easier in terms of learning this average that we never give to the model. And I have very few minutes, and I want to at the end talk about heavy tail generative modeling. Recently, I've been applying also some of the things that we've learned in the visual domain to model weather data. So I know probably very few people know what is weather. So I mean, weather data, you can think of it as just images. And weather prediction is kind of like generating videos over time, right? So if you want to build generative models to, for example, to do weather prediction, there are some instances that you need to really care about. Like heat waves are kind of extreme temperature values, or atmospheric rivers are like extreme rainfall. Typhoons or hurricanes are extreme wind speed, right? So if you want to learn a generative model, they're at the tail. And that's what matters, right? What is peak there is a boring sunny day in California. What's there over there, it's some heat wave or extreme weather event that you need to be able to predict or model well with these generative models. We looked at diffusion models on how well they can capture heavy tail distribution. So here we have this two example where by definition, one dimension, like this dimension, is designed to be Gaussian and other dimension is designed to be heavy tail. Now, if you train diffusion model, something interesting happens. The dimension that is Gaussian, it actually learns the histogram really well. The other dimension that is heavy tail, it struggles with capturing the tail on the other dimension, right? So this basically shows that Gaussian diffusion models, they struggle with generating tail of the distribution. So we showed that actually by changing the diffusion process, rather than using Gaussian diffusion, we use student T distribution that has heavy tails. And we showed that using that now, you can capture these tails really well. This was a paper that was published at iClear 2025 this year, and it's called Heavy Tail Diffusion Models, if you want to check it. So yeah, this brings me to the final slide. So I think if we think about what's after diffusion, whatever it is, it needs to keep what we have already, which is high quality sample generation, stable training, coarse to fine, maybe inductive bias for the image and visual domain, and control and guidance. But it also needs to give us what we are missing, which is something like fast sampling, efficient training, as well as being able to model the training data distribution well. So if you're thinking and if you have ideas how to tackle, I would say, yeah, keep going and yeah, share some ideas. Thanks.
Yeah. So unfortunately, we don't have enough time because we're going to the next speaker. But thanks again, Arash, for the really great talk. So the next speaker will be
Thank you. Thank you.
So Ricky is a researcher at instead of diffusion models, but now
Do you have the adapter?
yeah. So this two both can work.
Sure.
One second.
Yeah.
This one.
Do you wanna?
Yeah, let me try about this one. It says choose to mirror or let me stop sharing. Oh, I think it's here. Allowed. And then
Maybe I'll just try again.
yeah, let me just try it on.
With it plugged in.
Yeah.
Yeah. So share entire screen. Okay.
Then, because this one is not for sharing, so it's kind of like you're presenting here and also you share a screen on the Zoom. So the sharing is not working very well.
Oh.
It just we didn't we'll get you in the on here. Maybe we can try the other side. Sure, the type C. I could okay, can you also like open the
Yeah, hold on. I think I know what's wrong. Yeah.
Okay. Display. Six. Various switch displays, but seems not connected to that as well.
Mirror extend to one of these?
Yes, maybe let's try Miro, maybe. This one? No, it's not none of this actually.
Yeah.
Weird. It seems you're not connected to that display. Let me try the okay. Let's allow it to allow. Oh, but why after I allow it, it's what up?
I can try using someone else's MacBook.
Yeah,
Send over the
yeah,
keynote.
fine. Okay, send me the slides or sure.
Oh. Oh, wait, I think I found it.
Okay, you can find it. Oh,
There we go.
okay, great.
Okay, don't look at my mail. Oh, I need to share screen on Zoom too, right?
Yeah, you share screen.
Yeah, my bad, my bad. All right, technical difficulties are over. Should I start?
Yeah.
Sure. Okay, cool. Yeah, sorry for the technical trouble. I'm Ricky, and when I was invited to this workshop, I was extremely excited because I saw the words "what's after diffusion," and I really wanted to talk about what's after diffusion. And then I realized a few days ago I have nothing in the visual domain to talk about because I'm not a computer vision scientist, and this is my first time at CVPR. So bear with me a little bit. I'm going to talk about a little bit about language modeling and discrete, and continuous and discrete, and maybe in the future bring everything back to the vision domain, or you guys help me do it. Okay, so my talk's about unlocking discontinuities in flow models, or let's say diffusion models or Markov models, what have you. And why do we want to do this? It just sounds, not that important. Well, you can do this to introduce jumps. You can do this to introduce branching factors like control flow. You can also use this to introduce like insertions and deletions to modify dimensions, right? So unlike Arash, who talked about all the practical insights about why, what's wrong with diffusion, I don't actually know too many practical insights, so I just went with what's literally wrong with diffusion. And they cannot do these things right now. So a little bit about me. I was part of this team who created flow matching, which is a bit of a controversy, but anyway, so flow matching is a nice argument, I think, and I'll talk about why I think. So why this recipe, the derivations for doing this can generalize to discontinuities and jumps and stuff like that. And we apply this to this model called Meta Movie Gen, which is like something really at scale for generating video and audio. Basically, I needed to put some vision in here in the talk. And then I'm also working on things like we call it reward driven, which is we don't really have data from the target distribution, but we have some reward that we want to be optimizing. And the best way to achieve this usually is like you sample from the model and try to figure out how to update the model to do better. But it's really extremely slow. And recently we've been creating methods that are like extremely fast at just sampling from unnormalized distributions without seeing any data. And it does much faster than previous works. But that's not what this talk is about. This talk is about things that are not visual, but things about like generator matching. We're going to go through 3 works called generator matching, discrete flow matching, and edit flows. And basically, generator matching is the version that is generalizing flow matching, ODE, SDE into something a bit more general. And basically, you have to be creative in order to use it. So we were a little bit creative and created these, this edit flow at the end, which allows insertions and deletions. So we'll get there. All right, so generator matching. I know everyone's familiar with this, but just to set the stage, what is generative modeling? We typically want to go from noise to data, okay? And the stage that I'm setting right now is we want some sort of continuous interpolation. So, not normalizing flow, not GANs, just some sort of like continuous interpolation of the density that slowly, morphs from one distribution to the other distribution. And, we have different ways of modeling this. We can either model this we always model this with a vector field right now, but we can also sample either with just a vector field or we add a little bit of noise and sample it as a stochastic differential equation as well. Now, these are things that people are very familiar with. And once you discretize it across time, you can think of this as like there's some sort of transition kernel that every single step is updating my sample until eventually it arrives somewhere. But these models are currently only based on local perturbations. And I don't really like the way that diffusion models are handling noise right now, because the noise is purely isotropic, because it's just completely independent in every single dimension. You can sort of use it as like a way to do search or like add some randomness. But basically what's happening is, there's some sort of diffusion happening, dispersion, right? And then the vector field is handling higher contraction to sort of bring it back to the original distribution. Right. Instead, what we should do is like, okay, if I wanted to go somewhere else, maybe I should be more intelligent about where I should go. I should be like, okay, my location is not good. I don't want to keep, doing ODEs from here. My model says, okay, I need to get closer to the data distribution at this point. Maybe we should just directly jump all the way over there, right? So the jump process that I'm going to talk about is at every single iteration, you either stay locally where you are or keep flowing or something like that, or there's a chance of just completely jumping to somewhere completely random. Not random, but like determined by the model, learned by the model itself, right? And if you take this jump process and just quantize the same space or like, apply in discrete space, you get what people call discrete diffusion, or we call it discrete flow matching models. But basically the process is called a continuous time Markov chain. So discrete space, continuous time. Okay. Now, the generator matching starts up with this sort of like really theoretical thing. I'm not going to go into the theory, but one nice way of viewing it is you take a kernel that is, a one-step kernel that predicts xt plus h given xt, and you take a look at the derivative and you take the time, at the step size goes in 0, right? You take the infinitesimal limit. And the first order is you just stay at xt, right? The second order, the 0th order is stay at xt. The first order is this thing that we call the generator. And then the rest is just some error that once you take h small enough, you can sort of ignore. There's something really nice about the first order approximation. And really, this is what I think is allowing, for example, diffusion models to be trained very, very stably. Okay. So just to give you some examples, I'm not going to work with the generator. It's a very complicated concept. But the ODE, basically, it's just a vector field, right? So the first order approximation of some sort of like a flow, some sort of deterministic trajectory, right? It's just a gradient of that. And the SDE is, in the usual case, is you include some sort of Brownian motion, some sigma t that is not state dependent, just time dependent, although it could be state dependent as well. And finally, the last line, what I want to talk about, it is this jump and CTMC process, where you either stay at the current point or we basically completely resample from this UT. Okay, so let's break down this process and what it looks like. What this UT is and the way you should think about it is it's not a direction anymore because there's not, it's not really based on the metric. It's just an unnormalized distribution. It's a distribution over your entire space or like a subset of the space, and its normalization is not 1. It doesn't integrate the 1 over the entire space. And so one way you can interpret this is that there exists a normalized distribution proportional to this called Q, and what's left over is the normalization of that UT, right? So what is happening now is if you plug this back in, the first line is essentially a mixture model, right? You either stay exactly at this delta distribution at xt, or there's a probability of sampling a new location from the QT, okay, from the Q model. Okay? And so if we just look at this algorithmically, this becomes a bit clear. There's a weight, which is 8, the step size times lambda. And if, with that probability, I'm going to sample from Q, and that's my new state. It's a completely new state. It's not necessarily local, not necessarily anywhere. We get to sort of define the support of Q itself. But otherwise, if we fail that coin toss, we stay at XT, right? This looks like stochastic, it's fine, but just, we also do things like top case sampling, CFG, we can make this deterministic as well. So there are tricks that we can do to sort of make this branching factor, this if statement, maybe more heuristic. If I have multiple ways of branching, I could take, for example, the one that the model is most confident about, the one that's the size lambda. So just to give you a little bit of sense, why I think this is control flow, it is technically we define it sort of like a rejection sampling scheme, something that looks like that. But in practice, we can apply heuristics and it'll look much like a branching factor, a control flow. And yeah, I think it looks kind of cool. We don't know what to do with it yet, but it looks kind of cool. All right, so how do we train this thing, right? And I want to say we train this exactly the same way that we do flow matching. Okay, so flow matching is, I think most people understand this as you take a data point, you take a noise point, you look at some linear interpolation, and then you learn a vector field that just points towards the data point, right? And so we call this, there's a conditional probability path that's sort of like converging towards the delta around x1, and apologize, x1 is the data, not the noise. And there's a conditional vector field that we regress onto, right? And so in flow matching, we said, okay, well, if you want to just marginalize over the data distribution, or let's say, as Arash said, be very mean to the model and average over all the data points, you get this probability path that is interpolating between the noise and the data distribution. And if we take this conditional expectation of this conditional velocity, we get a velocity that transports from the distribution of noise to the distribution of the data. Okay, so flow matching looks like this. And really, the whole reason why it looks like this, I would say, you can say it's due to the score and relations like that, but I would say it's all due to the linearization. It's the first order approximation of some stochastic process. And so, oops, I skipped a slide. And so you can do exactly the same thing to the generator, which is what we're talking about, that little Q, that unwise distribution that tells you where to jump. Okay, you can again say, let's have a conditional generator. I didn't explicitly say what this is, but just assume like as time goes on, there's some x1 that we want to basically sample. So every time I jump, I want to get closer and closer to that x1. So there's, these jump points are just like, purely discrete. It's not a continuous perturbation anymore. And again, we average the exact same quantity, this first order approximation. Okay. And so our theorem says basically for the case of like flow matching or diffusion, I think people call it bridge matching, the marginal generator, the marginal velocity will generate the marginal probability path. So it's going to follow the correct probability path and eventually hit the data distribution. And the same thing for the jump process, and we're going to call it the CTMC process as well. The exact same recipe follows. Okay. So the flow matching laws, as sort of you would typically know, is there's a regression problem, right? You do MSE and you try to regress onto the conditional vector field. This gets you an unbiased gradient of just regressing directly to the marginal vector field because the solution is the conditional expectation. There's a generalization of this as well. So instead of using the MSE loss, we can actually just plug in an arbitrary loss. Sorry, not arbitrary, but it must be a Bregman divergence. So we looked into this because lots of people have been thinking, okay, should we be using like L1, like a GAN style, like, what are some guarantees that we can say that it'll still have the right optimal solution if we were to change the loss function? And we basically proved an if and only if statement that if your loss is a Bregman divergence, your optimal solution doesn't change. Okay, and this is useful. We'll get to that later because U is going to not be a vector field. It's going to be a whole distribution. So we'll use other Bregman divergences for training the jump process. Okay. But in general, this is quite of a nice little trick that you can try to think about. If you ever want to learn a conditional expectation, just use a Bregman divergence. It includes the whole family of things you might want to do. And it actually does include, if you want to stay close to the theory and also make practical design choices, it includes this function phi, and you can choose phi to be whatever you want. If phi is just it needs to be a convex function, but if it's just the L2 norm, for example, this will recover the MSE. You can use, the L1 norm in there and recover something. You can put in the cross entropy, it'll recover the elbow. So there's many different instantiations of this. All right. So just a toy, just to show like what this looks like. Here's usually how we design a probability path that goes between some noise and some data. It's the checkerboard distribution. And we can learn a model. We can learn a flow model. We can learn a jump model. We can just basically combine the flow and the jump together. And they'll all follow the same probability path because that's what we trained it for. But the sampling paths are all very different, right? So if you look at the red one, that's the pure ODE. It's going to just only do like deterministic transformations that are very, very smooth. The jump process basically just jumps. Basically, we made it jump only one dimension at a time. So that's the blue line. And then we can also do a combination. We can say if we don't jump, let's just go with the flow, right? Because it's also updating my particle to the next time step. I can just arbitrarily combine these things. And then you get this blue line. This green line. Basically, one nice thing about this sort of we call this as Markov superposition, but you can take a Markov jump model, Markov flow or diffusion model, and just combine the two of them. And one nice thing is sort of you can think about if you randomly sampled a noise, it could be a noise that is not good, right? If you just do ODE sampling, it deterministically determines what the sample would be. And so maybe during the sampling process, you'll be like, okay, I'm kind of in a weird location that I'm going to transport to the weird location in the data manifold. I want to suddenly jump to a different location. That's what the model is saying. The model says, if I'm too far away from where I should be, lambda goes up. That's essentially what's going to happen in the model. And so the jump probably goes up and I resample from somewhere and get maybe closer to the data distribution that I want to sample from. Right, so what we found useful is sort of we tune this a little bit, we do more jumps at the very beginning, and then the flow is sort of like making it very sort of refining the distribution at the very end. This works okay-ish. Again, not a computer vision. We just did, CVPR10 and ImageNet 32. But if you combine the two, it does work pretty well. We also did this multimodal distribution. It's for proteins. So I'll already skip this, but if you look at the animation, you can sort of see how we applied this. At the very beginning, there's a little shiver. That shiver is the jump process. And then we turn it off. And then we just said, let's just keep flowing. Right? And this did much better than, a little bit better than if you just only use a flow model. Okay. All right. So that's kind of interesting. I don't know if there's really a huge significant, application for adding shivers to your sampling process. But the idea of using jumps is quite nice, and we've been developing this for mainly the discrete domain, which is why I haven't really been working on vision for a while. But if you think about the discrete domain, I'll bring this back to vision in a bit. But if you think about the discrete domain, we want to be generating like text and sequences of tokens, right? The vocabulary size can be like 150,000, and I want to generate like 2,000 of these tokens. So UT should be this normalization, the distribution over like complete sequences, right? But the sequence distribution is just way too intractable. Yep. It's in the wrong order, but yeah. So if we would directly say I model every single probability to every single other sequence that I could get to, it's just way too intractable. And so what we usually do for this discrete and also discrete diffusion, mass diffusion, is we just make this axis aligned, this independent assumption where we only modify one token at a time, right? So if you think about the graph over sequences, all the nodes are only connected by one token changes. Okay, and we just we traverse that graph. Again, the same thing sort of happens where if I have a distribution or like some way of defining this UT that just converges to a single point. And here it's really, really simple. There's a jump rate that is increasing. It's going to infinity at time 1. If you haven't jumped, you really got to jump. And where it jumps to is just x1, right? So it's really, really simple. It's like a mixture model. It's you just see x1. The first time you jump, you just go directly to x1. There's no real corruption process happening. It's just unmasking. And so you do the same thing. You can marginalize the same recipe. Holds here. And this is just a visualization that discrete flow happening. So on the left, it's not like in the continuous space where there's some sort of transport, right, of the distribution. It's just a mixture model. It's just like the noise is going down, the target's going up. So it's maybe not that interesting. There's no metric to it. But this is something that we can easily apply for text because we don't have a good metric for text. Okay. So we did this, this is about last year. We said, let's take a mask model, which is also very, very popular now. But basically, if we knew exactly how many tokens we wanted to inpaint at a certain location, and we want to condition on like not just the left, but condition on whatever direction we want, we can use this sort of like a mass diffusion model to say, let's just sample the tokens, unmask the tokens, right? So a lot of works on this like simple, effective, simple, and simplified and generalized mass diffusion. Sort of gone down this round. There's been lots of works, Lada, Dream, about scaling this up to like 8 billions. Kind of works pretty well. I personally don't really like it. I want to work on something a little bit different than the mass construction. So one little thing here is that I said that currently there's no corruption process because it's not really mainstream. We had a work previously about sometime end of last year where we tried to include a corruption process in the sense that you have some sort of like distance metric between two different token values. And when I denoise, I just want to get closer. I don't want to go directly to X1 because maybe it's hard to predict. I just want all my tokens to sort of get closer towards X1. So more like a continuous, flow diffusion kind of style. And we basically derived saying, okay, if you design any sort of probability path, you can design this based on any sort of metric you want, like a metric D. I can give you a velocity that you want to regress onto, that you can do. You can plug into the Bregman divergence. And I'm not going to show you our results because our results are not that good. But this is a result recently from other people from Hong Kong that applied that same method to multimodal generation. So basically in the image space, they used like some VQVAE embeddings to define the distance. And then for text as well, they used embeddings from their own multimodal model to define distance. And so when you look at this, like when it's trying to answer a question, they think of this as like reasoning or like thinking. It's not exactly explicit reasoning tokens that you throw away. It's just during the generation process, you're kind of like trying to get closer and closer to the solution. You're not really there. And so there's, it generates maybe noisy tokens in the middle, but it's a way to scale compute. And it doesn't have any sort of like mass tokens. You just start from random tokens. Okay. All right. And the last thing I want to talk about, I think I went a little bit fast. Yeah, oh, actually I'm good. Okay, so the last thing I'm going to talk about is imbuing diffusion with dimensional changes, right? So now we're getting to the interesting stuff, and I think I'm much more bullish about this than the little squiggles. So let's talk about that. Yeah, okay. So when we generate variable length sequences, really the sequence is not fixed dimensional. It's the union of tokens to the power of n, where n could be some number. And we previously said, okay, if we want to do discrete diffusion, we just said, okay, let's just do alignment, right? But we don't really want to be aligning tokens because it doesn't really make sense, right? We want to be thinking about things like edit distance or like, because sequences are sort of like, temporally, not that stringent, right? So when people do, for example, the mask diffusion to generate variable length sequences, they pad it a lot with these n of sentence tokens, these special tokens just for padding. But this also has downsides. It makes the model more overconfident in predicting the n of sense token because it just appears so many times. And what they end up doing is they do semi-autoaggressive sampling. So they don't do the hierarchical, non-autoaggressive sampling anymore, just because they needed this padding. Okay. So what we're going to do, actually, yeah, sorry. So there's been a lot of works. This is, I think, pre-LM era-ish, right? And a very rough description of these prior works is they sort of train using like sort of imitation learning. There's a sequence of edit operations that get them to the thing that they want, and they basically train like a Markov model or like an autoaggressive model that just like directly tries to predict that sequence of edit operations, right? But the sequence doesn't matter. Usually there's like we should view it as a set of edit operations, and usually there's a two-stage model where you first predict the number of edits, and then you create a new model where you have like placeholders or mask tokens, and then you do causal a causal mask model to try to predict what tokens to insert at those locations. So there's like a two-stage process. So our model is sort of, I would say, conceptually a little bit simpler, and sort of we try to pull it into this, this flow matching, generator matching framework, where essentially this UT is, instead of like one token changes, like one token replacements, we allow one token insertions and one token deletions, right? So there's a graph of sequences, and when two nodes are connected is when there's one edit operation difference between the two sequences, okay? So what that means in terms of parameterization is when I give it a sequence, I want to have some sort of rate, some unrealized probability for all my neighbors, right? And all my neighbors are basically, at each location, what is my, I can insert, any one of the tokens or substitute this into one of the tokens or delete it, right? And the generation process just kind of looks like this. You do some edits on the sequence. We're gonna, of course, also do this all in parallel because we sort of output different edits for different locations. So if the model is very, very confident about doing 2 edits at the same time, like I'm almost finished generating a sentence, I just know there's something missing here, some other token missing there, I can just generate both at the same time, right? So it's still got that non-autoaggressive flavor. Now, the main thing that's hard to make, it makes it hard to train is there's multiple ways to map XT to X1 now. Previously, we aligned them perfectly. We said, okay, this sequence goes to that sequence, and so I need to turn every single token into that. If it's not the same one, I need to modify it. But now, if I allow insertions and deletions, there's basically a very, very large number of possible. Like I can insert a bunch of random garbage and then just delete it. So it's like infinite number of ways to map from XT to X1. Right. So the way we handle this is sort of very, very similar to how diffusion models works. Is you don't optimize you introduce latent variable, but you don't optimize them. You just like use it as is. So we're gonna do the same thing. We're saying, okay, let's call these things alignments, which is basically the padded versions of my X0 and my XT. And so here's an example where I want to go from kitten to smitten. The first one on the left is the most optimal alignment. There's only 2 edit operations. The one in the middle is sort of pat to the right, and this is what people would typically do if you use like a mass model or like a fixed dimensional model. And then the third one's also kind of interesting, is like you delete everything and just reinsert everything. But basically the alignments, the Z0, Z1 uniquely define the set of operations that map from X0 to X1. And now we can just use what we've learned before, the mixture model, right? To sort of define the training process. Our model doesn't see the masking at all. Our model doesn't see these epsilons just in it, right? So it's kind of like intuitively, it's like building the padded sequence, but then having the model only see the truncated sequence that removes all the padding. Okay. I'll skip this in the interest of time. I think this is something a bit interesting. So I showed you that very unreliable coupling of deleting everything and just reinserting everything, right? So we tried a little toy experiment where we just like deleted everything from X0 and reinserted everything. And we asked the model, when the model generates from X0, what's the distribution over X1s? So similar in the continuous case, we always see that there's a collision happening, right? So kind of like what Arash said, if you arrive from this XT and there's multiple X1s that arrive at this XT, you need to make a decision. Usually there's like some sort of like rule, symmetry breaking happening during sampling. And so similarly, something's happening here as well, where the model is like, okay, well, I want to map from like AAAA to AAAA. I shouldn't be doing any edit operations at all, right? So the model is learning something a bit more optimal than the training signal. And so it's inheriting the same sort of behavior from flow matching in continuous space as well, which I thought was interesting. So in this initial work, we basically just did image capturing from scratch. This is like some animation of the text being generated. You can see it's sort of like, if it reloads, okay, maybe it doesn't. But anyway, there we go. So it's like generating first maybe the things that it obviously sees, it's high confident about from the image, and it's sort of like filling in these places, right? And also one nice thing about this sort of process is you never get left over with like half a word. Whereas the mass model, if you try to generate these sort of things, you kind of have this awkward alignment where like you need to determine the value, token value based on exactly what position it's in. Whereas this one, I just know like there's going to be a cat somewhere, I can just throw it over there, and then afterwards self-correct, the sample itself. We also did this for sort of medium, I think small scale, we call it now, text to and code generation. And basically the top one is if we have an insert only model. The bottom one is like we have you can think of it as like a Brownian bridge, where we also insert some random stuff in the middle and then ask the model to delete it. But basically you can start from like any sort of like a wrong code and ask the model to like project to the data distribution kind of, right? Kind of like energy-based models. And oh yeah, and for the code, it kind of works. For the text, I think we're almost like pretty much at the autoaggressive level. For code, we're still pretty far away from autoaggressive, but it beats better. It's a little bit better than the mask. It's something we're still working on. I do think I'm pretty bullish about this, so I'm gonna we'll see. We'll see in the future. Okay, so a quick summary about that. So I basically said, if you sort of try to understand the flow matching recipe, there's some vector field, you want to like regress onto that. You could do exactly the same thing, but now you learn this like jump process where you parameterize an unnormalized distribution. Of course, you need to make it so that it's tractable in some sense. And during sampling, we have this sort of branching factor. And basically the training signal is you just need to learn a conditional expectation. It is something positive, so we don't take the MSC, we take like a cross entropy sort of thing. We take a log. So you can look at the details in the paper, but yeah, basically the way that we look at this, it's not like derived through the elbow, which is what typically people would do for discrete diffusion. We just say, it's a functional thing. We just want to learn a conditional expectation. And so here's a set of loss functions you can use. And yeah, I just wanted to thank all my collaborators. This is a pretty, I think, a long line of work that we've been trying to pursue, and hopefully we also make it somewhere in the future, and also maybe bring it back to vision. I think there's lots of nice sequences we want to do, maybe not for images, but like for video and audio for sure. It makes sense to generate these sequences in a not altogether manner, but also, you need to handle the variable length somehow. Okay, thank you.
Okay. Yeah, so like we don't really have time for question and answer, but thank you again for introducing this very interesting flow models to us. And our last speaker will be Liang, Chen. So actually, Liang you wrote the
What is that?
Oh, why does it?
That was gonna be just you rejoins. I don't know. Or
doesn't work again.
Yeah, it's not working. You go back here again, just click here again.
Okay. So let's start with T-Talk. T-Talk was introduced in our newest 2024 paper, and image is worth 32 tokens for reconstruction and generation. Here is the motivation of our work. So 2D VQ-VAE is the typical approach to quantize images into 2D discrete tokens. It adopts an auto-encoder framework. We have encoders and decoders. So if input is 256 by 256, and the downsampling rate is a factor of 16, usually you will end up with a 16 by 16 discrete tokens, and those discrete tokens are arranged in a 2D grid structure. So if we zoom in, so basically the model is trying to perform per page quantization. For each page, we will find its nearest neighbors in the codebook. Okay, so far so good. This setup, each tokens will maintain a strong spatial relationship with the tokens. Let's take this top left token, for example. It will correspond directly to the top left image patch. So there's a strong spatial relationship. This 2D graph structure, therefore, fails to exploit the image redundancy. Recent works, such as Max Autoencoder, MAE, have shown that we can reconstruct the images using 25% or even fewer, like 5%. You can still reconstruct the image patches. So therefore, in this work, we asked, do we really need so many image tokens to represent the images? So to answer the questions, we propose transformer-based one-dimensional tokenizers, T-Talk. It's a very simple but effective framework. It contains 3 components. First, the vision transformer-based encoder that takes the image patches and the latent tokens as input. And the latent tokens will be used to compress to learn the image representations. Second, we have VQ-GAN quantizers that will quantize the latent tokens into discrete values. Third, we will have a vision transformer-based decoders that takes the max tokens and the discrete tokens as input and learn to reconstruct the images. Super simple. So to summarize, we have a T-Talk encoder that basically condenses the images into a few latent tokens. You can use 32 tokens, 64 tokens, and so on. Those tokens can be used to reconstruct images. Even more, with those 32 tokens, we can train a burst dial max transformer to predict the randomly maxed tokens. Then you have a generative models. In this slide, we try to visualize the reconstruct images with T-Talk. On the axis, we value the number of latent tokens. We value from 16, 32, 64, and so on. On the y-axis, we show that we value the transformer size from small base to large. As you can see from top left, the subfigure, even with only 16 tokens and a small transformer size, we can still reconstruct the salient part of the images. And as more and more tokens are used, final details will be recovered. Okay. So on the ImageNet 256 benchmarks, our models surprisingly can perform or even outperform, perform comparably or even outperform diffusion transformer-based models. And when using only 32 tokens, our model can run 169 times faster. And on the ImageNet 512 benchmarks, because the SPR will be more significant, because the image is larger and there will be more redundancy. When using only 64 tokens, our model can run 410 times faster. Now let me share with you our generative result, even with only 32 tokens. 64, 110, yeah. As you can see, even with only few tokens, we can still generate very good images. So recently, we tried to extend these frameworks to text-to-image generations. We propose Chieh T-Talk, text-aware T-Talk. It's a similar architecture to previous model T-Talk. We have vision encoder, VQ-GAN quantizers, and the vision transformer-based decoder. But additionally, we use the text token encoded by the clip text tower, use them as input to the detokenization. These tokens will provide the high-level information to guide the image reconstruction. Let me share with you some of our reconstruction results. So given a captions and original images, our previous model TTalk failed to reconstruct the fine details of these two images. With the guidance of the captions, TTalk can successfully reconstruct those regions. Now, let me share with you some of our cool generated results with the text guidance. And on the NJHQ 30K benchmarks, our models can also outperform previous state-of-the-art methods like stable diffusions while only using open data. And our model can train much faster than stable diffusion and the pixel art alpha, and also runs much faster. So, sorry, so still. So I would like to share with a concurrent work with all of you. It's called Test Talk. It's a concurrent work published at CVPR2025. They actually adopt a similar work to our framework. They extend TTalk to text token as input, but they text token to both encoder and decoder. So our TTalk framework has been extended to other exciting texts by the community. First, real-time digital humanoid agents that enables interactive conversations. So you can basically generate the 32 tokens on the fly because only few tokens. Or video generation, you can extend the same framework to videos. Now the input is not only the images, but a clip of frames. Or dynamic token length. Recently, people has proposed to use a single tokenizers to dynamically generate different number of tokens. You can even tokenize the image into just one token. Or even cooler. So this is a paper on arXiv a few days ago, text-guided editing in the impending. They discovered that our 32 tokens actually demonstrate strong semantic meanings, and you can manipulate those latent tokens to do text-guided editing or even impending. Okay, let's pause a little bit. Can you tell me what are those images reconstructed by 32 tokens? And what are those images reconstructed by 256 tokens? First row?
Top 256.
Top 256, okay.
Bottom 256.
Bottom 256. Okay, help. So actually the first row is reconstructed by 32 tokens. So as you can see, even with only few tokens like 32, we can reconstruct the image quite well. Okay, let's talk about our second and third works, XAI and AIA. So in this work, we are trying to ask different questions. So in previous talk, people asked what's wrong with diffusion. So now we're trying to ask what is wrong with autoregressive models. Okay. So to have to better benchmark this, again, we resort to ImageNet 256 generation benchmark. On the y-axis, we show the FID, so the lower the better. And we categorize the generative models into three groups: autoregressive models, best transformer models, and latent diffusion models. And if you check the best performing variants in each category, you will notice there's a huge gap between AI methods with the other visual generative model. So what's wrong with autoregressive models? Autoregressive model is the de facto approach for natural language processing. It basically predicts the words sequentially from left to right. But why autoregressive models perform worse for visual generation? So can we apply the same principle to visual generations? Meaning we have image patches and we flatten it into 1D sequences and it generates sequentially. Can we do this? Probably not, right? So we think there are at least three challenges in adapting autoregressive models to visual generations. First, the scanning order. Because image is 2D by nature, how can we scan the images? So the pioneer work Jiaming transformer has proposed multiple scanning orders, such as raw major. spiral in, spiral out, or Z-curve, or subsample, or alternate. Okay, tons of scanning orders. Which one is better? It's hard to say. Second, information density. We already know that images has large redundancies. We can reconstruct the images with only 5% of the image patches, for example. On the other hand, text has denser information. So BERT pre-training usually only masks out 50% of the text tokens. Third, training strategy. Autoregressive models are usually trained with teacher forcings. This stabilizes trainings, but somehow cause the so-called exposure bias, meaning the model will struggle during inference because the model has no access to ground truth tokens anymore. He can only rely on its predictions. Okay, to summarize, we think there are at least 3 challenges in adapting autoregressive models to visual generations: scanning order, information density, and training strategy. Let's talk about scanning order. So previous work has explored a lot of scanning orders. Which one's better? We don't know. So we propose random order. We randomly permute it. Okay. So the methods proposed in our recent work randomized autoregressive visual generation. How does it work? We have image patches. We tokenize as before, so flatten it into 1D sequences, and then we randomly permute it. Okay, because of the permutations, we need some guidance to the model. So we add target-aware position embedding to tell the model where is the position of the next token to predict. And then we do next token prediction as usual. And with this simple trick on the ImageNet benchmark, it significantly bridges the gap. Okay, but if you think carefully, you will know this somehow randomized permutation somehow makes sense. Because if you check max transformer or diffusion, in their self-attention module, they actually use bidirectional attention. And this random permutation will somehow introduce the different context for the model. So you will train the models to use different contexts to predict the current token. Okay. Also, I would like to share with you another concurrent work. RAN-AI is also accepted to CVPR 2025. It's a very similar work to our methods. They also propose to randomly permute the 1D token image token sequences. But instead of adding the target-aware position embedding, they concatenate it with the image tokens. All right, so let's talk about the second challenges, information density. I will focus on our recent work beyond next token, next X prediction for autoregressive image generation. So in the traditional AI methods, they do next token prediction. Given 2D image tokens, we flatten it into 1D sequences and do next token prediction. Okay. So in this work, we propose XAR is use next X prediction. Well, is this framework? Okay. Next X prediction. So X is a general prediction entity. It can be either an image token similar to you will fall back to previous autoregressive models, or a cell which is a K by K grouping of neighboring tokens, or a subsample which is a non-local grouping of distance image patches, or images, or scale like a cost to find resolutions. So what does that mean? Let me show you some visualizations. When X is equals to tokens, it falls back to the previous vanilla autoregressive models. When X is the cell, you basically have a larger groups of cells, or a subsample, non-local grouping, or images. Then you fall back to diffusion or flow-metric models. Or next scale prediction, you predict from coarse resolution to final resolutions. Okay, so we propose a general framework, next X prediction, and X can be lost entities that we play with. So in our experience, it turns out that next cell predictions performs the best. So why is that? Why next cell predictions better? We think there could be a few reasons. First, this next cell predictions shifts from isolated local token prediction to predict local coherent patterns. Okay, and also now the local patterns will encode not only the small details like edges, but also regional context, such as object parts. Simply put, a cell will contain denser information than a single image token. Okay. Let's go to the last training strategy. So remember that typical autoregressive models will use teacher forcing, meaning they will use ground truth tokens during trainings. And this will stabilize training, but exposure biases, the model has no access to the ground truth tokens during inference. It can only use its own predictions. And if prediction is wrong, the error will accumulate. To solve this problem, we propose noisy context learning. And let me illustrate the process with you. Okay. So given images, we partition it into a 2x2 cells. And for these 4 cells, we randomly sampled 4 time steps. And we also sampled 4 Gaussian noises. And then we compute the interpolated inputs as in traditional flow matrix. Okay, nothing new. And this could be probably the only equation I will share with you today. Okay, so basically we try to add some noises for all the cells. And we put all the cells, noisy cells, as input to the autoregress transformer. And then we try to estimate the velocity of current cell. So compared to previous teacher forcing, you will use all the clean cells as conditions. Now we will add a little bit noise to the conditions. So basically, noisy context learning transitions from previous discrete token classification to continuous entity regressions. So this again is the illustrations of how noisy context learning will perform. You add a little bit noise to previous cells. And during inference, XAR will first predict the current cell from Gaussian noises. And then given these estimated clean cells, we estimate current cell from another Gaussian noise as well. So this process will repeat it in an autoregressive manner. Okay, so to summarize, in XAR, we have played with multiple types of prediction entities, and it turns out that cell is a good prediction entity. It provides one advantage, denser informations compared to single token. And we also propose noisy context learning to mitigate the exposure bias. So it's a very simple approach, just add a little bit noise to previous tokens as conditions. So with these 2 simple tricks, XAR further push the boundaries of autoregressive models. So on the ImageNet 256 benchmarks, our heavy variance XAR-L and XAR-H outperforms previous methods like diffusion transformers. Our lightweight model variant XAR-B performs slightly better than diffusion transformer, but it runs 20 times faster. And notably, we do not need to use any vision foundation model like Dino V2 as used in the RIPA. Okay, to conclude, going beyond diffusions, we have focused on 3 recent works. First, T-Talk, we propose a compact tokenizations. We want to revisit the 2D tokenizations. We try to remove the image redundancy and have a compact representation. And to improve the autoregressive modeling, we propose RAR and XAR. RAR use the randomized permutations to train the models to exploit multiple direction contexts instead of unidirectional contexts. And in XAR, we export different prediction entity. And also we propose noisy context learning. Finally, I would like to thank all my collaborators. This work would not have been possible without their dedication, creativity, and also hard work. Thank you.
Okay, so that actually concludes our today's workshop. Thank you everyone again for coming to this workshop. I hope that you still learn something like beyond diffusion models. And yeah, that's it. Thanks.
Wait, how can I leave?
You just leave the. Let me see. I don't know how you can leave actually. Let's show this.
Yes.
Stuff.